I like to start with a picture I can feel in my bones, so imagine the entire universe is soaked in an invisible medium, like a perfectly clear honey that fills all of space. I don't mean a gas or a mist you could scoop into a jar, I mean a quantum field, something that has a value at every point in space and time and that never ever turns off. I'm talking about the Higgs field. When particles try to move through this field, some of them glide more easily, some of them drag as if their boots are stuck in molasses, and that drag shows up in our equations as mass. That's the key idea. Mass is not just a number we tack onto particles, it emerges from their interaction with a field that is on everywhere. The Higgs boson is the tiniest ripple, the quantum twitch of that field. If the field is the ocean, the boson is a single wave crest popping into existence for a heartbeat and vanishing again. Let me get more concrete. In the Standard Model, which is our best tested recipe, for the known particles and forces except gravity, every fundamental particle is described by a quantum field. Most of these fields can be zero in empty space. But the Higgs field is special. Even in what we naively call vacuum, it keeps a non-zero value. Physicists say it has a vacuum expectation value. I'll use a number in everyday language. That value is about 246 giga electron volts, usually just called 246 GeV. An electron volt is a tiny unit of energy, if you like. Mass units, energy divided by the speed of light squared, converts to mass because of E equals mc squared. So when I say GeV, think energy scale, and through Einstein's relation that corresponds to a mass scale. Now, when a particle like the electron couples to the Higgs field, the strength of that coupling is a simple number called its Yukawa coupling. The larger the coupling, the more the Higgs field resists the particle's motion, and the greater the mass the particle acquires. In plain words, electron mass equals its Yukawa coupling times the Higgs field value divided by the square root of 2. Said slowly for voiceover, mass equals coupling times V divided by root 2. Heavier fermions like the top quark just have a bigger coupling. It's the same mechanism scaled up. I think one of the most beautiful pieces of this story is the idea of spontaneous symmetry breaking. Before the Higgs field chooses its non-zero value, the equations respect a kind of perfect symmetry between certain particles and forces. After the field settles into a non-zero value, that symmetry is hidden, not destroyed, hidden like a round wine bottle that looks identical as you spin it, until you set it down on a table and pick one spot to press a label. The shape physicists draw to explain this is the famous Mexican hat potential. Imagine a circular ridge with a dip, like the brim of a hat, and a raised center. The top point at the center would be the perfectly symmetric state, but it's unstable, like balancing a pencil on its tip. The field rolls down into the circular valley around the center and sits there. Picking a point on that circle breaks the symmetry and gives mass to the W and Z bosons, the carriers of the weak force, while leaving the photon massless. That's why light travels huge distances without slowing down, while the weak force is short-ranged. The photon doesn't couple to the Higgs field, the W and Z do. Has the Higgs boson been discovered? Yes. Yes, it has. On July 4th, 2012, two enormous experiments at CERN's Large Hadron Collider ATLAS and CMS announced a new particle with a mass of roughly 125 GeV. That's about 130 times the mass of a proton. They saw it in decay channels like 2 photons or 2 Z bosons that themselves decay into 4 charged leptons, which are beautifully clean signatures in the detectors. Those first hints grew into strong evidence and then precise measurements. Over the years since, the particle's properties have been measured again and again, and they match the predictions for a standard model Higgs. It's a spin-zero, parity-even boson. It couples to other particles in proportion to their mass. And its total natural width, the intrinsic lifetime, imprinted as an energy spread, is only a few million electron volts, about 4 MeV, which is razor thin compared to its mass. Look at how audacious this is. We predicted a field to explain how particles get mass without wrecking the mathematical consistency of the theory. And then we found its quantum ripple, right where the equations pointed. If you like the nuts and bolts of how we make Higgs bosons, here's the short tour. Inside the LHC, protons are accelerated to energies of several tera-electron volts each. That's trillions of electron volts, and smashed together 40 million times per second. Higgs bosons appear mainly through gluon-gluon fusion, where two gluons from the protons interact via a heavy quark loop dominated by the top quark and produce a Higgs. That's the dominant production mode. There are others, vector boson fusion, where two weak bosons radiated from the quarks collide to make a Higgs, associated production with a W or Z boson, and associated production with top quarks. Each mode leaves a different fingerprint in the detector. We then infer the presence of the Higgs from its decays to two photons, to two Z bosons, to two W bosons, to a bottom quark pair, to a tau lepton pair, and more rarely to even lighter states. The standard model gives us branching ratios, probabilities of each decay path, and the data so far track those ratios closely. So the thing we found isn't just any new particle. It behaves like the Higgs must behave for the rest of the standard model to hang together. Now I want to talk about the mathematics in a way that's friendly to a mic. The potential energy that governs the Higgs field's behavior can be written in words like this: a number lambda multiplied by the square of the magnitude of the field squared minus v squared over 2. If you expand that in your mind, it says there's a price for straying from the circle of minimum energy, and the curvature at the minimum determines the mass of the Higgs boson itself. Translate that. The mass of the Higgs boson roughly equals the square root of 2 times lambda times v. Because we know v is 246 GeV, and we measure the Higgs mass to be about 125 GeV, we can back out lambda, which comes out to around 0.13. That's a small but not tiny number, and it's one clue in a larger question. Is our vacuum truly stable forever, or only metastable, meaning it could in principle tunnel to a lower energy state over cosmological timescales? With the measured top quark mass and Higgs mass, the math suggests we live near a boundary between stability and metastability. Don't panic. Near, in this context, still means unimaginably safe on human timescales, but it's a profound hint that high-energy physics could be delicately balanced. I sometimes get asked whether the Higgs boson gives mass to everything. Not quite. Most of the mass of ordinary matter, the stuff you and I are made of, comes from the energy stored in the strong force binding quarks into protons and neutrons. The quarks themselves get their rest masses from the Higgs field, yes, but the lion's share of a nucleon's mass is the churning energy of gluons and quark motion inside. So the Higgs isn't the source of all mass, but it is the mechanism by which elementary particles, leptons and quarks, and the W and Z acquire their rest mass terms in the equations. Without it, those particles would be massless in the theory, and the weak force would look nothing like it does. Where does this leave us? We've checked dozens of boxes. We've measured Higgs couplings to W and Z, to bottom quarks and tau leptons, and we have evidence for its coupling to top quarks via production. Each measurement, so far, lines up with the standard model expectation that the coupling strength is proportional to the particle's mass. Proportional, in plain words, means double the particle's mass, and you double the predicted coupling strength. We've also looked for exotic decays into invisible particles or unusual combinations that could hint at dark matter or new forces. So far, no smoking gun. The total rate and the pattern of decays look wonderfully, infuriatingly normal. But normal, at this level, is a kind of miracle. It validates a framework that took decades to build. Still, my scientific instinct won't sit still. I want to know if the Higgs talks to the dark sector, if it has siblings, if it's composite rather than elementary, if its own self-interaction, the Higgs self-coupling that determines the shape of that Mexican Hat Valley, is exactly what the standard model says. The self-coupling shows up when the Higgs boson produces another Higgs through its own interaction with itself, which can be probed in double Higgs production. Those events are rare. You need huge statistics. At the energies and luminosities of the LHCs run 2 and run 3, we've begun to nibble at that measurement. The high luminosity LHC will push further, and next-generation colliders, linear or circular electron-positron machines, designed as Higgs factories, or even higher energy proton colliders, could measure the Higgs properties to the percent level and beyond. The dream is to turn "we found it" into "we know it like a friend." Let me do one more bit of math, in plain words, because it carries intuition. The electron's mass is about half an MeV, which is 0.05% of a GeV. The Higgs field value is 246 GeV. Rearranged, the electron's Yukawa coupling must be its mass times root 2 divided by V. That works out to roughly 3 in 10 million. Tiny. The top quark's mass is about 173 GeV, so its Yukawa coupling is roughly 1 of order unity. Same formula, wildly different numbers. The Higgs field is impartial. It treats every fermion according to its coupling, and those couplings are just parameters we measure. Why those numbers are what they are, why the electron is so ridiculously light compared to the top quark, is a deep flavor puzzle. We name the problem, we don't yet own the solution. Sometimes people worry that the Higgs discovery was the end of particle physics. I think that's backwards. It closed a chapter that had an obvious missing page. The page is now in place. Now we're reading between the lines. If there are additional Higgs bosons, as many theories beyond the standard model suggest 2 Higgs doublet models, supersymmetry, composite Higgs scenarios, they would change the pattern of couplings and the rates of certain processes. If the Higgs mixes with a singlet that's invisible to our usual forces, some of the time it would slip away into hidden decays, and we'd see less than expected in the visible channels. If the Higgs is a portal to dark matter, we might catch it in events where energy seems to go missing because something neutral and non-interacting carried it away. The quiet power of precision is that even if new particles are too heavy to make directly, they can tug on the Higgs through quantum loops and leave small correlated fingerprints in the numbers. Small. Small doesn't mean unimportant. Small can be decisive. So what is the Higgs boson? It's the quantum of the Higgs field, which is the mechanism by which electroweak symmetry is hidden and elementary particles acquire mass. Has it been discovered yet? Yes. And not just discovered, but weighed, catalogued, and within current precision, found to be exactly the kind of scalar particle the standard model ordered. I'm satisfied, but I'm not done. The next decade is about measuring its couplings to the percent level, pinning down its self-interaction, and hammering at every seam where new physics could be hiding. If the universe has chosen to whisper rather than shout, the Higgs is the right ear to press against the door. I'll leave you with one last image that sits with me whenever I think about this field. We live inside a crystal of sorts, a universe where the vacuum itself has structure, where empty space is not empty, where every electron in your body and every quark in every proton is constantly in conversation with an invisible background that lends them heft. The Higgs boson is our hello back, a brief, delicate syllable from the vacuum when we hit it hard enough in a collider. We asked a yes or no question in 2012. The universe said yes. Now we're asking it to elaborate, carefully, quantitatively, relentlessly, until the pattern either matches perfectly or the slightest mismatch tells us where to dig next. I want to press deeper into what it means for a field to hide asymmetry, because that's the engine room of the Higgs story, and it's easy to say the words without feeling the gears. In the electroweak theory, we begin with a gauge symmetry that treats several force carriers on equal footing, a symmetry elegant enough that all the carriers would be massless if left alone. But that tidy world isn't ours. When the Higgs field settles into a non-zero value everywhere, three of the would-be massless excitations, three Goldstone modes, don't appear as particles you can catch. Instead, they are eaten by the W maze, W mains, and Z to the power of zero bosons, giving those force carriers their longitudinal polarization and with it their masses. That eating metaphor is more than cute. It's the mathematical statement that the degrees of freedom that would have shown up as massless pseudoscalars now show up as the extra components of massive vector bosons. The photon remains aloof and massless, which is why electromagnetism reaches across galaxies while the weak force dies away in less than the width of an atomic nucleus. I think this is one of the crispest examples in physics where something we call nothing the vacuum decides how far a force can reach. Because we measure everything, let me translate these ideas into quantities a detector can love. The W bosons weigh about 80 GeV, the Z weighs about 91 GeV, and the photon weighs exactly 0. Those numbers aren't slapped on. They follow from the interplay between the Higgs field value and the electroweak couplings. When we say the Higgs boson has a mass of roughly 125 GeV, we're reading the curvature of the Mexican hat potential where the field sits. Curve steeper, particle heavier. Curve gentler, particle lighter. We infer couplings by watching how often the Higgs decays to various final states. In a single sentence of math, in plain voice, the predicted probability that a Higgs decays into a given pair is proportional to the square of that pair's coupling to the Higgs times the phase space available. That's why decays to heavy pairs like bottom quarks are common, about a little more than half of all decays, while decays to photons are rare, much less than 1 in 100, because photons couple only through loops of charged particles. A collider is a statistics machine, so I also owe you the logic of discovery in numbers you can narrate. Suppose I expect B background events in a clean region of my analysis, and I observe S plus B events in the real data. A back-of-the-envelope measure of surprise is S divided by the square root of B. If that ratio is about 5, we call it a 5 sigma effect, which in simple probability language corresponds to a chance of a few in 10 million that a background fluctuation faked the signal. The real analyses are far more careful. They build full likelihood functions that depend on nuisance parameters. They fit shapes rather than just counts, and they combine independent channels with correlated uncertainties. But the intuition remains that signal big compared to the jitter in the background is what convinces a hard-nosed community. That's why July 4th, 2012 mattered. 2 separate experiments with different detectors and different analyses both saw consistent humps in places the standard model said they should appear. Let me make the ephemeral concrete with lifetime. Every unstable particle has a width, a tiny spread in its measured mass that encodes how quickly it decays. The Higgs width is around a few million electron volts, while its mass is around 125 billion electron volts. To translate width into a lifetime, you say this sentence: lifetime equals Planck's constant divided by the width. With a width of a few MeV, the lifetime is roughly 1.6 times 10 to the minus 22 seconds. In human words, it exists for 100 billionth of a billionth of a billionth of a second, then it's gone. That is why we never see a Higgs directly. We infer it from pristine debris, like 2 high-energy photons pointing back to a common origin. Production and decay are a dance of probabilities, so I like to anchor them with orders of magnitude. Most Higgs bosons at the LHC come from gluon-gluon fusion. Call it the lion's share. A smaller but precious fraction come from vector boson fusion, where two quark jets frame a central Higgs. That topology is a godsend for background rejection. You can also make a Higgs alongside a W or a Z, or together with a top quark pair. Those associated productions are rarer but exquisitely informative because the accompanying particles tag the event. On the decay side, picture a pie. The fattest slice is bottom plus anti-bottom, then come W pairs and Z pairs, then gluon pairs and tau pairs. Charm is smaller, photons are sliver thin yet incredibly clean, and there are loop-suppressed oddities and invisible possibilities we keep chasing. The pattern, the whole cake, not just a slice, has matched the standard model within present uncertainties. That's not a shrug, that's a non-trivial check that the Higgs couples to mass, not to electric charge or whim. People sometimes ask whether neutrinos join this feast through the same door. In the simplest standard model, neutrinos are exactly massless and don't couple to the Higgs at all. Nature, however, told us through neutrino oscillations that neutrinos do have tiny masses. One option is that they also have Yukawa couplings to the Higgs, but those couplings are stupendously small, far smaller even than the electron's already tiny coupling. Another option is that neutrino masses are generated by a different mechanism, such as the seesaw. Heavy right-handed partners with enormous masses leak a trace of mass into the light neutrinos we know, making them feather light, while the partners hide at unreachable energies. I like how humbling this is. The Higgs solved the mass puzzle for many particles, and yet left the neutrino story tantalizingly open for new physics. Now, for the elephant in the equations, the hierarchy problem. Scalar particles like the Higgs are beset by quantum corrections to their mass that, in simple words, try to drag their natural mass scale up to whatever the highest energy scale in the theory is. If we imagine the standard model valid all the way up to, say, the Planck scale, where gravity becomes strong, the quantum loops especially, those involving the top quark, would like to lift the Higgs mass sky high. To keep the physical mass at 125 GeV, you need a cancellation between the bare mass parameter and the loop corrections to many decimal places. That sounds like exquisitely tuned bookkeeping, and many physicists feel queasy about it. Supersymmetry offers a cure by pairing each particle with a superpartner whose loops cancel the dangerous divergences. Composite Higgs models suggest the Higgs isn't elementary, but a bound state of new constituents, protected by symmetries like a pion in QCD. Extra-dimensional ideas alter the way energy scales stack up. We've searched hard for the most obvious superpartners and the first rungs of compositeness without success so far. I'm not ready to declare naturalness dead, but I'm willing to let it evolve. Perhaps the tuning is real. Perhaps some subtler principle is at work. Another deep question ties the Higgs to the history of the cosmos. When the young universe cooled through the electroweak scale, the Higgs field slid from near the top of its hat to the valley. If that transition had been violently first-order bubble nucleation, walls colliding, it could have helped explain the excess of matter over antimatter through a process called electroweak baryogenesis. In the standard model, with a 125 GeV Higgs, the transition is a smooth crossover, not the dramatic bubble show we would need. That nudges us toward extended Higgs sectors. Add another doublet or a singlet, and you can make the transition first order, and perhaps create conditions for matter's triumph. On a different front, some theorists have asked whether the Higgs itself could have driven inflation with a special coupling to gravity. It's a bold idea. It requires the potential to be very flat at high field values. These cosmological connections are speculative but delicious, because they say the faintest shimmer in a detector might rhyme with the loudest events in the early universe. Precision is the path forward, and precision has a formula you can whisper. The expected number of signal events in a given channel equals luminosity times cross-section times acceptance times efficiency. Luminosity is how many collisions you delivered. Cross-section is the effective target size of the process, measured in barns, where one barn is a tiny area. Acceptance is the fraction of signal that falls into the detector's useful region. Efficiency is how well your selections and reconstructions keep those events. If you want to halve the uncertainty on a coupling, you usually need roughly 4 times the data, because many statistical errors shrink like 1 over the square root of the sample size. That is the motivation behind the high luminosity LHC. Pile up enough collisions to turn rare channels like the Higgs decaying to a Z and a photon, or double Higgs production into measurable staples. Double Higgs matters because it cracks open the Higgs self-coupling. In words, if the Higgs can shake hands with itself, the way the standard model predicts, 2 Higgs events should occur at a precise tiny rate. Any deviation is a neon sign pointing to new dynamics in the potential. I don't want to leave you with only proton colliders in mind. Electron-positron Higgs factories would produce clean, monochrome collisions where the background is far tamer. In that environment, you can reconstruct a Z boson on one side and infer the Higgs on the other, even if it decays invisibly, giving you model-independent handles on absolute couplings. Circular machines promise enormous luminosities. Linear machines can push energies and polarize beams. A muon collider, though technically ferocious, could combine point-like collisions with high energies and might even scan the Higgs width directly through S-channel production. Each machine has a distinct personality, and together they sketch a roadmap from "we found it" to "we have tested it from every angle." Let me circle back to everyday matter because it's a subtle point and worth saying cleanly. Your body's mass is not mainly a ledger of Higgs gifts, it's a ledger of QCD energy. The up and down quarks in a proton weigh only a few MeV each. 3 such quarks added naively don't come close to the quark's proton's 938 MeV total mass. The difference is the kinetic energy of quarks confined in a tiny space, and the energy stored in the gluon fields that bind them, both allowed to be called mass by E equals mc squared. The Higgs gives those quarks their tiny rest masses and gives the W and Z their heft, making radioactive beta decay possible and chemistry stable. But the bulk of what you feel on a scale in the morning is the thrum of the strong force. I find that grounding, mass is more than a number. It's a story about interactions. There is also a quieter frontier in the numbers, the running of couplings and the fate of our vacuum. The Higgs self-coupling and the top Yukawa coupling evolve with energy in a way we can calculate. With present best fit values, the Higgs potential at ultra-high field values seems to dip slightly below our current valley, implying metastability. If that holds exactly, our vacuum is long-lived beyond absurd cosmological times, but strictly speaking, not absolutely the lowest. The calculation is sensitive to the top quark mass by the second decimal place, so sharpening that input is not trivia. It changes the headline from stable to metastable to stable within errors. I don't lose sleep over it, but I do marvel that by weighing a particle produced in a European ring, we say something about the temperament of emptiness across the cosmos. Because you asked for math in a voice-friendly way, let me do 2 more quick translations. First, coupling, mass proportionality for fermions, can be spoken as coupling equals mass times root 2 divided by V. Say it slowly. Coupling equals mass times 1.41 divided by 246 GeV. Plug in electron mass about half an MeV and you get a coupling of about 3 times 10 to the minus 6. Plug in the top mass about 173 GeV and you get a coupling near 1. Same rule, wildly different outcomes. Second, convert width to lifetime again for intuition. If the width were 10 MeV instead of 4, the lifetime would be shorter by a factor of 2.5. Wider means briefer, narrower means longer lived. The Higgs is narrow, so it flickers and goes. Has it been discovered yet? Yes. And every year, since discovery, that yes has grown more precise. We have measured its spin and parity as 0 plus. We have established its couplings to vector bosons and third-generation fermions. We have first evidence of its fingerprints with top quarks in production. We have glimpses of rare decays, and we have upper limits on invisible or exotic branching fractions that already squeeze many speculative models. We haven't yet nailed the self-coupling with the precision we crave. We haven't mapped second-generation couplings, muons are emerging, charm is hard. We haven't excluded subtle mixes with hidden singlets. That's not a disappointment, that's an agenda. So, what is the Higgs boson to me, after all the algebra and apparatus? It's a permission slip, the universe writes, to let fields be massive without breaking the symmetries that keep our equations renormalizable and predictive. It's the quantum quiver of a field that never turns off. It is also a door. If there's a hidden sector of the dark matter that outweighs us 5-1, or new forces that barely graze ordinary matter, the Higgs may be the polite handshake across the threshold. I imagine the vacuum not as a void, but as a medium with a character, and the Higgs is how we learn to hear its accent. I think the next act is not waiting for a single dramatic shout, but learning to hear correlations at the 1% level, the subtlest harmonics that whisper, there is more. Until then, I'll keep saying the simple truths out loud, because they're still astonishing. A field fills space. Its value gives mass. A brief particle proves it. I want to tug on the thread of why the Higgs had to exist at all, not just as an aesthetic flourish, but as a guardian of consistency. If I imagine scattering two W bosons off each other at very high energy, think of ramming two tiny gyroscopes whose masses come from the Higgs field. There's a potential disaster in the equations. Without the Higgs, the probability for these WW interactions would grow with energy so fast that it would break a basic rule called unitarity, the simple statement that probabilities must add up to 1. Said in voiceover math, the amplitude for longitudinal W scattering would grow roughly like energy squared divided by V squared, where V is the Higgs field's vacuum value, 246 GeV. If that growth continued unchecked by energies of about 1000 GeV, the calculation would predict nonsense probabilities bigger than 1. The Higgs steps in as a counterterm written in reality. Diagrams with Higgs exchange interfere destructively with the dangerous pieces from the gauge bosons, and the leading growth cancels. In plain words, a scalar ripple of the field smothers the runaway and restores the math's sanity. I think this is one of the most satisfying reasons for the Higgs. It's not ornamental. It's essential to keep the electroweak theory predictive at high energies. There's also a crisp logic to how we determine the Higgs's spin and parity. Because we see the particle decay into two photons at an appreciable rate, we can rule out spin 1 by a theorem due to Landau and Yang. A single spin 1 particle cannot decay into two identical massless spin 1 particles like photons. That already narrows the options to spin 0 or spin 2 and up. Then we look at the angular distributions in decays to 4 leptons via 2Z bosons. A scalar with positive parity predicts a specific, gently symmetric pattern of angles and invariant masses among the leptons, while a pseudoscalar or a graviton-like spin 2 state would imprint different, skewed patterns. The data marching step with a spin 0 parity even assignment, what we call a scalar with quantum numbers 0 plus. Said compactly for the mic, not vector, not graviton-like, scalar and even. Before I wander farther into experiment, I want to ground the symbols in one identity I love for its economy. The Fermi constant, G sub F, which measures the strength of low-energy weak processes like muon decay, is directly related to the Higgs field value. In words, you can say on camera, V equals 1 divided by the square root of the square root of 2 times G sub f. If you plug in the measured G sub f, you get V about 246 GeV. This identity is the handshake between old-school weak physics and the Higgs mechanism. It says the scale of the Higgs field is what sets the overall size of weak interactions in the first place. I like that it collapses several chapters of particle physics into a single sentence you can speak slowly and clearly. Now let me take you inside a detector, because we saw the Higgs is easy to say and hard to earn. Picture a cylindrical cathedral of technology. At the core, a silicon pixel tracker that records the minuscule curves of charged particles as they spiral in a magnetic field. Around that, electromagnetic and hadronic calorimeters that catch and measure the energy of particles by absorbing them in dense materials and sampling the resulting showers. Outside, a muon system that tracks the clean, penetrating muons that fly through meters of steel, almost unfazed. When a Higgs decays to 2 photons, you never see the boson itself. You see 2 bright, needle-precise clusters in the electromagnetic calorimeter, with energies and directions that, when you add the 4 vectors like little arrows, produce an invariant mass near 125 GeV. Stack millions of such pairs from ordinary processors under the same selection, and most make a smooth hill of background. If there is a Higgs, a small bump rises above the hill at the right place. That bump, that little asymmetric shoulder at 125, is the sighting. It's humbling. The universe whispers through a statistics plot. 4 lepton decays, the so-called golden channel, are like a physicist's lullaby. 4 charged tracks in the inner detector, 2 pairs each with an invariant mass near the Z mass, and their combined invariant mass peaking again near 125 GeV. The background here is low, which is why that channel delivered some of the earliest clear events you could print out and hang on a wall. Bottom quark decays are messier because quarks shower into jets. There, we lean on techniques that find tiny displaced vertices. Bottom hadrons live long enough to travel about a millimeter before decaying, leaving a subtle kink of tracks that don't point back to the exact beamline. Algorithms called B-taggers catch those signs, and multivariate methods, fancy ways of combining weak hints into a stronger, discriminant, separate signal from copious QCD backgrounds. I emphasize this to make a point. The Higgs story isn't just a clean stroke of theory, it's a test of craft, instrumentation, calibration, and statistics tuned to hear a quiet note in a loud room. Let's visit production for one more layer of intuition. Gluon-gluon fusion, the main source, works through a virtual heavy loop with the top quark doing most of the lifting. If we had a world with a different top quark mass or an extra heavy quark that couples to the Higgs, the rate would change. Because we know the observed rate, we can turn that logic around and constrain the existence of exotic, heavy-colored particles, even if they are too heavy to produce directly. Vector boson fusion draws a different picture. The forward jet's thin, energetic sprays of hadrons escaping at shallow angles flank a central, relatively quiet region where the Higgs pops and decays. Select events with 2 such forward jets, a large rapidity gap between them, and a modest amount of extra activity in the middle, and you enhance your signal to background. Associated production with W or Z bosons is precious when chasing the bottom quark decay, because tagging the accompanying W or Z gives you an extra handle to suppress QCD noise. Associated production with top quarks is a direct way to feel the top Yukawa coupling in your fingers. If the Higgs truly talks to mass, it should be loquacious with top. A question I love for its innocence and bite is whether the Higgs couples identically to particles and antiparticles, or whether it misbehaves subtly and violates CP symmetry. In the standard model, its interactions are Cp even, but if there were even a small Cp odd admixture, a little tilt in the scalar's personality, it would show up in carefully constructed angular correlations among decay products, or in the polarization patterns of vector bosons in production and decay. Searches so far lean strongly toward the pure Cp even case, but the limits leave a sliver of room for a mischievous admixture. This matters beyond cataloging personalities. New Cp violation could help explain why the universe has far more matter than antimatter. I want to clear a common misunderstanding with a two-sentence parable. Many headlines said, "The God particle" for clicks, but the Higgs is not a sacred talisman. It's a mathematically necessary piece of a gauge theory that describes the weak force in a way that works. The nickname started as a joke in a book title. It stuck, but it muddies more than it clarifies. If anything, I prefer calling it the Y-mass particle, and then immediately amending that with the earlier caveat: the Higgs gives mass to elementary fermions and to W and Z bosons. The mass of protons and neutrons is dominated by strong force energy. Because you asked for math you can speak, let me give you two more compact relations. First, the relation among the W boson mass, the Z boson mass, and the weak mixing angle, theta sub W, in the tree-level standard model reads, in words, m sub W equals m sub Z times the cosine of theta W. Loop corrections modify this, and those corrections depend on the top quark mass and the Higgs mass. That's why, before discovery, precision fits from older experiments already preferred a relatively light Higgs. The numbers wanted it. Second, the rate for the Higgs to decay to 2 photons, though rare, depends on a delicate cancellation between loops of W bosons and loops of top quarks. The W loop dominates and gives a positive contribution. The top loop subtracts. If there were a new heavy charged particle, say, a charged scalar or a vector-like lepton, it could join that interference pattern and slightly tweak the 2-photon rate. So when we measure that rate to a few percent, we're fishing for whispers of new charged states beyond direct reach. I think it's fair to ask whether the Higgs is elementary or composite. In composite Higgs models, the particle we call the Higgs is more like a pion in QCD, a bound state of deeper constituents held together by a new strong force. The Higgs's lightness would then be explained by it being a pseudo-Goldstone boson of a broken global symmetry, naturally light even in the presence of heavy dynamics. These models predict partners vector-like quarks, resonances in WW scattering, deviations in couplings that grow with energy. We've chased several such signs. None has yet obliged. But the energy reach and precision will keep improving, and compositeness remains a coherent, testable idea, not wishful thinking in fancy clothes. A quieter but equally sharp place to look is the second generation. We have strong evidence for couplings to third generation fermions, bottoms, taus, and the top through production. But the charm quark coupling is slippery. The charm's decay products are hard to tag with confidence in the busy environment of a proton collider. The muon coupling is cleaner, and I'm delighted that we have now seen the Higgs decaying to muon pairs, corresponding to a coupling 600 times smaller than for the tau, exactly as mass proportionality predicts. Saying it in the preferred cadence, coupling equals mass times √2 divided by v. Muon mass is about 105 MeV, tau mass is about 1770 MeV. The ratio of couplings should match the ratio of masses. The data say yes within uncertainties. Charm is coming into focus through clever strategies like tagging charm jets with machine learning and exploiting associated production, where kinematics help. Each successful second-generation measurement squeezes alternatives and affirms that the Higgs talks to mass universally, not selectively. On self-interactions, let me paint the stakes again. The shape of the Higgs potential, the depth of the valley, and the curvature along the valley's floor is encoded in numbers called self-couplings. The cubic self-coupling determines how likely a Higgs is to split into two Higgses in our diagrams, which shows up as a small excess of events with pairs of Higgs decay products, two bottom pairs, or bottom pair plus photons, or other combinations. The standard model predicts a very small rate for double Higgs production at current energies. To measure it precisely, we need enormous integrated luminosity and very sharp control of backgrounds. The payoff is grand. That one number tells us whether the valley is carved exactly as a simple quartic potential says, or whether it's dented by effects from higher scales. If the dent exists, it could be the footprint of new heavy fields, or even the trace of the universe's electroweak phase transition being first order rather than a smooth slide. I also want to nod to an exquisite experimental fact that hides in plain sight. The Higgs is narrow. Its natural width is only a few MeV, which is far smaller than the mass resolution of our detectors in most channels. We can't resolve the width directly by simply looking at how spread out the mass peak is. Instead, we infer the width by more subtle methods, like comparing on-shell rates, where the Higgs is produced near its mass, to off-shell production in processes like 2Z bosons at masses above 200 GeV that are still partly fed by virtual Higgs exchange. The ratio of these regimes carries information about the width. That we can even attempt this is a testimony to the maturity of collider physics. We are weighing whispers against whispers and coming away with numbers. It's natural to ask whether the Higgs could be a portal to dark matter. If there exists a new stable neutral particle that couples to the Higgs, something like a scalar singlet or a Majorana fermion with a Yukawa-like link, then some Higgs bosons should disappear into invisible final states, nothing but a slight imbalance in momentum, inferred as missing transverse energy. We look for this in events where the Higgs is produced together with a visible companion like a Z boson decaying to leptons. So we can say with confidence a Higgs was likely here, and then notice that the Higgs itself left no trace. So far, the fraction of such invisible decays is constrained to be small. Small is not zero. Small still leaves room for models where dark matter shakes hands with the standard model through the Higgs, but does so quietly. Behind all these quests is a rhythm that repeats across physics: predict, detect, refine. The prediction was the Brout-Inglet-Higgs mechanism, born in the 1960s from the need to give mass-to-gauge bosons without wrecking gauge symmetry. The detection came in 2012, with two independent experiments seeing concordant bumps. The refinement is this long, careful decade of measuring couplings, spins, parities, widths, rare modes, self-interactions, and possible leaks into the unseen. I think the refinement phase is where subtlety lives. The universe has already shouted yes. Now, we're grading its handwriting to see if the loops curl exactly as the textbook says, or if there's a flourish that betrays a different teacher. If you want one more piece of voice-friendly math to tuck in your pocket, keep this. The expected number of Higgs events equals luminosity times cross-section. If your luminosity is 100 femtobarns inverse, and your cross-section for a given channel is 50 picobars, multiply the numbers in plain language. 100 times 50 gives 5,000 events before cuts. Then multiply by acceptance and efficiency, maybe a few tens of % each, and you wind up with hundreds to a couple thousand analyzable events. Every factor in that sentence is a knob we can turn with better machines or better methods. Better luminosity with upgraded accelerators, better acceptance with refined triggers, better efficiency with smarter reconstruction, better background suppression with more incisive features, and cleaner theory predictions. Progress is not magic, it's multiplication. So what is the Higgs boson now that I've circled it from unitarity to detectors to couplings to cosmology? It's the smallest tremor of a field that gives structure to the electroweak world. It's a validator that our method of weaving symmetry and its breaking actually maps onto nature. It's a probe whose delicate interactions let us test for shadows of heavier things we can't otherwise touch. Has it been discovered yet? Yes, decisively. And the more precise question, the one that keeps me gladly restless, isn't whether it exists, but whether it is exactly the Higgs we wrote down, or the first clue to a deeper layer. I'm content to be patient and rigorous. If there's a deviation at the 1 or 2% level, it will not escape a community that has learned to hear decibels in a hurricane. Until then, I carry 3 sentences like a charm. A. Field fills space. Its value gives mass. Its ripple is real. I want to lay my hands on the scaffolding that lets us talk about small deviations without getting lost, because that's where the Higgs is becoming a precision instrument. The language we use is effective field theory, which is just a careful way of saying, I don't know the high energy details, but I can parameterize their low energy effects. In practice, I write the standard model as usual and then add higher dimensional operators suppressed by some heavy scale, call it capital lambda. Each operator is a mathematically legal combination of the known fields that respects our symmetries. The higher the dimension, the more it's suppressed by powers of 1 over lambda, so at LHC energies only the first few matter. In a microphone-friendly sentence, new heavy physics nudges the Higgs couplings by amounts proportional to energy squared divided by lambda squared. That scaling is why colliders are sensitive to heavy ghosts. They can't produce directly because the ghosts tug on the Higgs's behavior through these suppressed but coherent operators. I like how honest this is. We're not pretending to see beyond our reach. We're measuring handprints left on the wallpaper. There's a particular symmetry that keeps showing up like a guardian at the gate, custodial symmetry. At tree level in the standard model, the ratio of W and Z masses encoded in a parameter we call ρ is predicted to be very close to 1. Say it simply, ρ equals the square of the W mass divided by the Z mass squared times the cosine squared of the weak mixing angle. At tree level, it equals 1. Loop corrections and subtle effects tilt it a hair, but experiments say it's still extremely close to 1. Why does that matter for Higgs physics? Because any extension of the Higgs sector that mangles custodial symmetry would tip ρ away from 1, and we don't see that. So if you want extra Higgs doublets or triplets or something more exotic, you need to engineer them so they keep the custodial balance. This is a lovely example of precision measurements, quietly fencing theories in, not flashy, absolutely decisive. Let me reach for flavor, because why these masses for quarks and leptons is still a stubborn wonder. The Higgs gives a rule: coupling equals mass times √2 divided by V, but the masses themselves are input numbers, not derived. In the quark sector, we also have mixing encoded in the Kabibbo-Kobayashi-Maskawa matrix, a set of angles and a phase that quantify how quark flavors change under the weak force. The Higgs couples in that flavor basis too, and in principle the couplings could misalign, leading to flavor-changing neutral currents at tree level, where the Higgs flips one quark flavor to another without changing charge. We do not observe such processes at any appreciable rate. That observation tells us that whatever mechanisms set the Yukawa matrices did so with a structure that's nearly diagonal in the mass basis, or that additional symmetries like minimal flavor violation are at work to suppress those dangerous flips. In plain words, the Higgs seems to respect the quiet boundaries of flavor to a remarkable degree. When we measure, for example, whether a Higgs ever decays to a bottom and a strange quark, we are testing the tightness of those boundaries. On the lepton side, I'm intrigued by the growing precision in the muon channel. We have now seen the Higgs decay to muon pairs, that is, a 600-fold softer handshake than the tau channel, because the muon mass is roughly 1/600th the tau mass. Saying the rule slowly for voiceover, coupling equals mass times 1.41 divided by 246 GeV. Plug in 105 MeV for the muon and you get a coupling around 6 times 10 to the minus 4. That a collider can fish that signal from the flood is a triumph of both design and patience. The next riddle is charm. If we can tag charm jets cleanly enough by their moderate lifetimes, their fragmentation patterns, and machine learning signatures, we can extract the Higgs charm coupling and close another loop on the mass proportionality story. I think this is where craft meets principle. The principle says proportional, the craft digs the proportionality from dirt. Let me lean back into unitarity with a wider lens. The WW scattering I mentioned earlier is one instance of a general rule. Amplitudes that grow too fast with energy must be tamed by either new particles or new cancellations. The Higgs is the new particle that rescues electroweak scattering, but the idea scales. If there are additional Higgs-like states, or if the Higgs is composite, the cancellations will adjust subtly as energy rises. That's why differential measurements, how a process changes with the energy or angle of the final state, can be more sensitive than total rates. In voice-friendly math, if a deviation scales like energy squared over lambda squared, then plotting the event yield versus a kinematic variable that tracks energy should reveal a gentle upward departure at the high end, even if the overall count stays within errors. This is the mindset of modern analyses. Carve the data into regions that emphasize energy growth, fit shapes, not just totals, and let the statistics tell you whether a slope is real. Because you asked me to speak math plainly, let me translate the Higgs potential into numbers you can hold. The usual textbook writes it as a negative mass term plus a quartic term. We already used that shape to explain the Mexican hat picture. Now, the cubic and quartic self-couplings of the physical Higgs particle, the ways it talks to itself, are tied to that potential. In standard model words for a mic, the cubic self-coupling equals 3 times the Higgs mass squared divided by V. The quartic self-coupling equals 3 times the Higgs mass squared divided by V squared. Put in 125 GeV for the mass and 246 GeV for V, and you get definite numbers. We can't directly plug an ammeter into the vacuum to read them. We infer the cubic coupling mainly from double Higgs production. The quartic is practically unreachable at current machines, but future colliders might glimpse it indirectly. The conceptual payoff is huge. Those numbers encode how stiff the vacuum is when we push on the Higgs field. Stiffness here is not poetry, it's the literal curvature and anharmonicity of the potential where the field rests. There's a subtlety I love that feels almost philosophical. In quantum field theory, empty space is a state, a specific choice with lowest energy given the dynamics. When we say the Higgs has a vacuum expectation value, we are declaring that the true empty state is one in which the Higgs field takes a uniform, non-zero value everywhere. Because fields and particles are excitations of one and the same entity, this choice permeates everything built atop it. The photon remains massless because its gauge symmetry stays exact in that vacuum. The weak bosons are heavy because that symmetry is broken. In a voice-friendly sentence, emptiness is not blank, it's structured, and that structure chooses what can coast and what must slog. I think that realization, emptiness with a personality, is the quiet revolution the Higgs brought from chalkboard to data. Let me return to detectors for a deeper cut, because the marvel isn't only theoretical. Mass peaks don't appear unless you understand your energy scales to within a percent or better. In the diphoton channel, that means calibrating the electromagnetic calorimeter with electrons from well-known processes like Z decays, correcting for minute material budgets in front of the calorimeter that make photons convert into electron-positron pairs, and tracking time-dependent responses as crystals, age, and electronics drift. In the 4-lepton channel, it means perfecting the momentum scale of muons, because a 0.1% bias will smear the peak and modeling the tiny tail of reducible backgrounds where a jet fakes a lepton. These things sound fussy. They are the difference between a rumor and a discovery. When we quote a Higgs mass with uncertainties of a few tenths of a GeV, it is because thousands of details behaved. A natural worry is whether we might be fooling ourselves with theory assumptions when we extract couplings. The community has been pushing toward model-independent fits, where instead of assuming every Higgs coupling scales by the same factor, we allow each to float separately within effective field theory constraints. The input is a tapestry, cross-sections in multiple production modes, branching ratios in many decay channels, kinematic distributions sliced by jet counts and rapidity gaps, and off-shell regimes that sneak information about the width. The output is a set of numbers with correlations. This coupling prefers to be 1.0, 2 plus or minus 0.15. That one is 0.98, plus or minus 0.2, with a negative correlation because of how rates multiply production and decay. Speaking those numbers aloud reminds me that Higgs physics is no longer a single bump. It's a global inference problem where every channel is a stanza in the same poem. On the cosmic side, I want to translate vacuum stability into something that feels less abstract. Imagine hiking along the rim of a massive caldera with a gentle slope inward and a gentler slope outward. Where you stand is locally stable, small pushes roll you back, but somewhere far away, the outward slope dips to a deeper basin. That's a metastable configuration. In math, you can speak the running of the Higgs self-coupling lambda with energy drifts slightly negative at very high scales, if the top Yukawa is big enough and the Higgs mass light enough. The sign flip means the potential curves downward for huge field values, opening a lower valley. Quantum tunneling from our valley to that distant one is possible in principle, but wildly unlikely within the age of the universe given the current best fit numbers. Sensitivity matters. Change the top mass by a GeV or two, and the curve of lambda with energy can stay positive all the way, restoring absolute stability. That is why metrology pinning down the top mass in a theoretically clean scheme isn't trivia. It's a headline about the character of the vacuum. Could the Higgs have siblings that hid in plain sight? Two Higgs doublet models add a second field with the same gauge quantum numbers, which after mixing produces 5 physical scalars, 2 neutral CP even states, 1 neutral CP odd, and a charged pair. One of the neutral ones must look like our 125 GeV friend. The others can be heavier and sneakier. Their presence would slightly rotate the couplings of the observed Higgs away from pure standard model values. Precision has already squeezed the allowed angles. Direct hunts for heavy neutral scalars decaying to tau pairs, or charged scalars decaying to a tau and a neutrino, comb the higher mass hills. Supersymmetric variants fit in this family too, with relations among couplings tied to the parameter tan beta, the ratio of the 2 vacuum expectation values. In voice-friendly terms, if there are cousins, they must be shy, heavy, or both. They have not crashed the party yet. Another place I keep staring is the Higgs plus a single photon, or a Z at high energy. These final states test loop-level subtleties and potential new charge particles in the loops. The 2-photon decay already told us the Higgs talks to charge through loops, not directly. Measuring the shapes of photon energy spectra and the angular distributions in these rare modes will tighten the noose around hypothetical partners. It's the same energy squared over lambda squared story with a photogenic face. Let me offer one more compact calculation you can say out loud, because it helps sanity check orders of magnitude. If the inclusive Higgs production cross-section at a given energy is say 50 picobarns, and your dataset corresponds to 100 inverse femtobarns of luminosity, then the raw expected Higgs yield is 5,000 events. Multiply by the branching ratio to 2 photons, roughly 0.2%, and you expect about 10 diphoton Higgs events before cuts. After acceptance and efficiency, maybe a few. That's why the first diphoton spectrum had a modest bump. Each event carried a lot of weight. In the 4-lepton channel, the branching ratios are even smaller, but the backgrounds are nearly absent, so a handful of events spoke volumes. In bottom quark decays, the branching ratio is fat, but the backgrounds are oceanic, so we rely on associated production and multivariate analysis to fish. What about the Higgs as a bridge to right-handed neutrinos or axion-like particles? If a light, weakly coupled scalar mixes a little with the Higgs, the 125 GeV state would borrow a tiny branching fraction into pairs of those light scalars, which might themselves decay to pairs of muons or pions with displaced vertices centimeters from the collision point. Detectors are getting good at triggering on and reconstructing such off-center signatures. A null result tightens the angle of allowed mixing. If the Higgs couples to invisible dark matter, we already said the invisible width must be small. Small does not mean uninteresting. A few percent invisible branching ratio would be revolutionary if nailed with certainty. And electron-positron Higgs factories are exquisitely placed to probe exactly that by recoiling against a reconstructed Z and counting how often the other side vanishes. I also keep a soft spot for the idea of a muon collider, not just for its audacity, but for a technical reason that fits our theme of speakable math. In an electron-positron collider, the S-channel production of a scalar like the Higgs is suppressed by the tiny electron Yukawa coupling. You mostly produce the Higgs with a Z. In a muon collider, the muon Yukawa is 200 times larger, and you can in principle sit exactly on the Higgs mass and produce it resonantly in the S-channel. If you can make the beam energy spread comparable to or smaller than the Higgs width, scanning across the resonance could give a direct measurement of the width and line shape, an otherwise inaccessible grail. Technically ferocious, scientifically sublime. Where does that leave the two questions you set me at the start? What is the Higgs boson, and has it been discovered? It is the quantized ripple of a field whose non-zero vacuum value hides electroweak symmetry and gives elementary particles their rest, masses in a way that preserves gauge, consistency, and unitarity. It is a scalar with spin zero, even parity, couplings proportional to mass, and a narrow width that makes it flicker out in about 10 to the minus 22 seconds. And yes, beyond reasonable doubt, it was discovered, first announced in 2012, and since then measured in an expanding web of channels with increasing precision. I think the more honest formulation now is this: we are past the is it there phase and deep into the is it exactly that phase. Every percent level test of a coupling, every slope at high energy, every null search for exotic decays is a chance for the universe to cough a nuance. If it does, we'll be ready to hear it. If it doesn't, that silence is itself a message that the Standard Model's austere elegance holds farther than many of us dared hope, and that the key to new physics may lie not in the Higgs's mischief, but in other corners of the map. Either way, the Higgs has taught us to treat the vacuum as a participant, not a backdrop, to treat mass as a dialogue, not a label, and to treat precision as adventure, not bookkeeping. I want to put my finger on the hardest part to accept emotionally, which is that the Higgs mechanism is at once deeply physical and maddeningly abstract. I can picture a magnet cooling and picking a direction of magnetization. I can picture a superconductor kicking magnetic fields out and letting electrons flow without resistance. Those are phases of matter born from collective behavior. The Higgs phase is the universe doing something similar with a quantum field that fills all space. I'm not saying the vacuum is a wire or a chunk of iron. I'm saying the mathematics of a symmetry you could see in the equations, but not in the ground state, runs through all three. In a superconductor, electrons pair up and condense. The photon picks up an effective mass inside and can't propagate freely. That's the Meissner effect. In the electroweak theory, the Higgs field condenses, the W and Z pick up true mass, and the weak force becomes short-ranged. Same melody, different instruments. I think analogies aren't proofs, but they earn trust. The Higgs is not a lonely trick. It's a member of a family of phenomena where emptiness becomes structured. Because you asked for truth warm plainly, let me make an accounting of what mass is where. For quarks and leptons, rest masses come from their couplings to the Higgs field. That's the Yukawa rule we've repeated. For W and Z bosons, mass comes from eating the Goldstone modes when the symmetry hides. That's the gauge boson story. For protons and neutrons, most of their mass is energy trapped in the strong force, the kinetic energy of quarks rattling around in a tiny volume, and the energy of gluon fields under tension, all convertible to mass through E equals mc squared. If you insist on numbers in words, 3 valence quarks in a proton contribute only a few tens of MeV total from their Higgs-given rest masses, while the proton's total mass is about 938 MeV. The rest is QCD. Your body's weight on a scale is mostly QCD energy. Yet without the Higgs, the up and down quarks would be massless in the equations, the weak interaction would be long-ranged and bizarre, and the path that led to atoms, chemistry, and stars would not resemble ours. The Higgs does not explain everything, but it sets the stage so that everything can happen in a stable, familiar way. I want to tell the story of discovery through the lens of doubt, because that's honest to how the field thinks. Before July 2012, we had a web of indirect clues. Precision measurements from earlier colliders, the masses of the W and Z, the top quark mass, the weak mixing angle preferred a relatively light Higgs when you fit the loops. The fit is literal. You write equations that predict observables as functions of inputs, then you adjust the inputs to best match the data. The best fit region kept pointing to a Higgs mass below about 200 GeV, and gradually, with better data, near the 120 to 130 window. But indirect is not direct. The Large Hadron Collider had to turn the whisper into a sighting. 2 experiments, Atlas and CMS, each weighing 7,000 tons of purpose, took turns peering into trillions of proton-proton collisions. The early years were a clinic in humility. Calibrate calorimeters, align trackers to microns, understand the way the underlying event sprays soft particles everywhere, and learn to distinguish a real photon from a neutral pion that imitates one by decaying to 2 super-close photons. Only then does a bump in the diphoton spectrum mean something. Only then do 4 leptons align into a narrow peak that refuses to go away as the data grow. Significance is the currency of discovery, so let me translate the statistics into speech you could put on a soundtrack. Imagine you expect B background events in a region of a spectrum, and you observe S plus B events in the data. A quick measure of surprise is S divided by the square root of B. 5 of those 5 sigma corresponds to a background-only chance down in the few in 10 million range. Real analyses don't stop there. They build likelihoods that use the full shape of the spectra, include systematic uncertainties as nuisance parameters, and sometimes combine channels with a technique nicknamed the CL's method to set limits when a signal isn't established. There is a lovely compact approximation for the discovery significance that you can speak slowly. Z equals the square root of 2 times the quantity s plus b times the natural log of 1 plus s over b minus s. It behaves like s over root b for small signals, but stays well behaved when s is not tiny. Whether you recite the simple ratio or the tidy log formula, the point is the same. Discovery is a competition between excess and jitter, and excess only wins if you have counted your jitters honestly. Let me open up the detector a bit more. Because the Higgs didn't emerge from equations alone. It emerged from pixels, crystals, gas tubes, and the geometry of a cylinder around the collision point. The innermost layers are silicon pixels, each a tiny diode that records a hit when a charged particle passes. Multiple layers let you build a curved track in the magnetic field, and thus infer momentum from curvature. The tighter the curve, the lower the momentum. Outside that sits the electromagnetic calorimeter, a lattice of dense material and scintillating or crystal layers that force electrons and photons to shower. You measure the light to get energy. Past that is the hadronic calorimeter for jets, then the muon system, big chambers that light up when a muon passes through tons of steel because muons are stubborn and don't shower easily. Triggers skim the flood, deciding in a few microseconds which events are worth permanent storage. At modern luminosities, dozens of proton-proton interactions happen in the same bunch crossing. We call that pileup. Untangling which tracks and energy clusters belong together is an art form now supercharged by machine learning. I think people underestimate how much of Higgs physics is software and calibration. A 1% miscalibration in photon energy would smear the mass peak beyond recognition. A poorly modeled fake rate would inflate or deflate a tiny excess into fiction. The discovery happened because 1,000 quiet details were tamed. You asked me to keep the math speakable, so I'll move to couplings as ratios. Experimentalists often quote signal strength, the observed rate divided by the standard model expectation. A signal strength of 1 means the number of events after all corrections matches the prediction. If you split by production mode gluon fusion, vector boson fusion, associated production with WZ, associated production with top, and by decay mode 2, photons, Z pairs, W pairs, bottom pairs, tau pairs, muon pairs, you get a grid of measurements. Each entry carries an uncertainty, and together they fit the narrative, coupling proportional to mass, vector couplings as predicted. Deviations so far are within error bars. Not every box is equally precise. The easy ones were measured first. The community then refined selections to isolate vector boson fusion with forward jets, or to tag B quarks with displaced vertices more cleanly, or to separate top associated production from lookalikes. The grid tightens. The poetry here is statistical. In the early days, a handful of diphoton and 4-lepton events wrote the word exists. A decade later, thousands of multi-channel events write the sentence it behaves. I want to talk about the look elsewhere effect because it's a subtle integrity check. If you scan a wide mass range for bumps, random fluctuations will occasionally look significant somewhere. The chance to see a 5 sigma fluctuation somewhere is larger than the chance to see it at a pre-specified mass. Good analyses correct for this by reporting both local significance, how surprising the bump is right where it occurred, and global significance, how surprising it is given the width of the search window. In the Higgs case, theory and indirect fits encouraged a relatively narrow window, and 2 experiments saw bumps near the same mass in multiple independent channels. That combination blunted the look elsewhere worry. Still, the ethos matters. We are allergic to fooling ourselves, so we quantify the ways nature could have fooled us if we weren't careful. Let me lift our gaze to the next decade, because has it been discovered is now a doorway rather than a destination. The high luminosity LHC will increase the dataset by an order of magnitude. That sheer luminosity turns rare processes into measurable ones. Double Higgs production, a whisper on a whisper, should become a number with error bars you can say out loud. That number maps to the self-coupling, how stiff the potential is when the field nudges itself. Rare decays like Higgs to Z plus photon or to a pair of muons cross the line from evidence to measurement. Differential distributions, how the rate changes with the transverse momentum of the Higgs, or with the separation of jets in vector boson fusion, tighten the net on effective operators that scale like energy squared over lambda squared. If there are small new physics nudges, they're most likely to show up as gentle slopes at high energy rather than as glaring rate shifts at low. Beyond the LHC, clean electron-positron machines promise a different style of certainty. You can reconstruct a Z boson cleanly and infer the Higgs on the other side from the recoil, independent of how the Higgs decays. That gives you absolute normalizations for couplings that are hard to pin down in a Hadron Collider's messy environment. A circular collider would deliver staggering luminosities near the Higgs-Strahlen peak. A linear collider can climb energy and polarize beams to disentangle left and right-handed couplings. A muon collider, technically fearsome, could in principle sit on the Higgs resonance in the S channel and measure the width directly if the beam energy spread can be tamed to MeV scale. Each machine is not just more data, it's data with different knobs, different systematics, different strengths. Together, they triangulate the truth. I'm not done with naturalness, because the hierarchy problem still shapes our intuition even as data have been stubborn. In plain words, quantum fluctuations of known particles try to pull the Higgs mass up to the highest scale in the theory. Keeping it nailed to 125 GeV looks like fine-tuning unless something cancels the pulls or forbids them. Supersymmetry pairs known particles with partners of opposite statistics whose loops cancel the dangerous pieces. Composite scenarios make the Higgs a bound state protected like a pseudo-Goldstone boson. Extra dimensions smear scales in clever ways. The most accessible superpartners, gluinos, squarks, winos, Higgsinos, have been hunted up to the TeV scale in many channels, and the null results have tightened the screws on the most economical models. That doesn't erase the idea. It shifts it to heavier, more compressed, or more stealthy spectra. Composite models face similar pressure from precise Higgs coupling measurements that so far hug the standard model. I can live with a world that is tuned. I can live with a world that is protected by a principle we haven't guessed. I can live with a world where the explanation sits at energies we won't reach in my lifetime. What I can't live with is pretending the question isn't interesting. Why this mass here and not dragged away is a sharp mathematical puzzle, not a vibe. Let's return to cosmology, because the Higgs touches history. When the universe cooled past the electroweak scale, the Higgs field's expectation value turned on. In the standard model, that transition is a smooth crossover. If instead it had been a strong first-order transition bubbles of true vacuum nucleating and colliding, the violent conditions could have helped create the cosmic matter-antimatter asymmetry through electroweak baryogenesis, provided there was also new CP violation. That line of thought motivates extensions of the Higgs sector that both modify the phase transition and introduce fresh CP violating phases. Those same extensions tweak Higgs couplings and open exotic decays. The comforting discipline here is that the early universe dreams are pinned to present-day numbers. If your model fixes cosmology but breaks precision Higgs data, it's out. If your model survives both, it earns more attention from direct searchers. Because you wanted math in a voice that doesn't scare, here's a compact identity I, love for weak physics. The Fermi constant Gf, measured beautifully in muon decay, is related to the Higgs vacuum value by V equals 1 divided by the square root of the square root of 2 times Gf. Spoken slowly, V equals 1 over the 4th root of 2 times Gf. Plugging the measured GF gives V about 246 GeV. This isn't a coincidence, it's the handshake between low-energy weak processes and the high-energy field that hides the electroweak symmetry. When I say the Higgs field value sets the strength of the weak force, this is the sentence I mean. Flavor deserves another minute because it hides quiet danger. The Yukawa matrices, the arrays of couplings that connect left and right-handed fermions to the Higgs, are the source of both masses and mixings. In a generic theory, nothing stops the Higgs from mediating flavor-changing neutral currents at tree level, like turning a strange quark into a down quark without changing charge. We do not see such things at appreciable rates. The tidy way to keep the peace is minimal flavor violation. The principle that the Yukawa matrices are the only sources of flavor breaking, so any new interactions must be built out of them in a way that preserves the observed hierarchies. In practice, that means dangerous processes stay suppressed by tiny known angles and masses. Measuring rare Higgs decays like Higgs to a muon and a tau, or to bottom plus strange, is not idle curiosity. It's a direct probe of how strictly the Higgs respects flavor boundaries. Null results so far say very strictly, with room for small mischief. I want one more pass through rare and invisible decays because they carry disproportionate meaning. If the Higgs decays to a pair of invisible particles, the simplest interpretation is that it sometimes turns into dark matter. The current upper bounds say that fraction, if any, is small, at most a few percent. Small, but a few percent of a cornerstone process would be seismic. Electron-positron colliders can measure that invisible rate model independently by counting ZH events, where the Z is fully reconstructed and the other side is missing. If an exotic light scalar mixes a little with the Higgs, we could get cascades like Higgs to 2 light scalars to 4 muons with displaced vertices centimeters from the collision. Triggers and reconstruction are now nimble enough to catch those signatures. The absence of such events chisels the angle of allowed mixing down. Each bound doesn't just close a door, it narrows the corridor toward the truth. Let me be concrete about yields again to keep scale in mind. Suppose the inclusive Higgs cross-section at your run conditions is around 50 picobarns. With 300 inverse femtobarns of data, a typical large run milestone, you expect about 15,000 Higgs bosons produced. 2 photons as a decay is about 2 in 1,000, so 30 raw diphoton Higgs decays before cuts. Acceptances and efficiencies slice that to the teens. 4 lepton decays are rarer still but clean. Bottom pairs are abundant in principle, but sit atop oceans of QCD jets. You need associated production with a Z or W, or vector boson fusion tags, plus sophisticated multivariate discriminants to carve out a signal. These are not Netflix numbers, they're cathedral numbers. Every event is a tile in a mosaic where the image appears only from far enough away. I'll end this round by looping back to your 2 original questions in the voice I promised. What is the Higgs boson? It is the quantized ripple of a field that never turns off, the field whose non-zero value hides electroweak symmetry and gives elementary particles their rest masses without breaking the mathematical spine of the theory. Has it been discovered yet? Yes, first announced in 2012 by 2 independent experiments, and since then interrogated in a dozen ways that keep saying this is a spin-zero parity even scalar with couplings proportional to mass and a very narrow width. The live question is not existence, it's exactness. Is it exactly the minimalist Higgs the standard model orders, or the first low note of a deeper chord? I think the way we find out is not by waiting for a thunderclap, but by accumulating decibels, percent level couplings, differential spectra at the high energy tail, self-coupling from double Higgs, rare and invisible decays squeezed to their natural bones, and cross-checks in machines with different personalities. If the universe hid a nuance in the Higgs, we will catch it by refusing to blink and by telling the truth with numbers as carefully as we can speak them. Thought, for 10 seconds, I want to pull on a quieter thread that ties the Higgs to everyday stability, because that's where this abstract field becomes a condition for our very possibility. Start with atoms. The size of a hydrogen atom, the Bohr radius scales, like 1 divided by the electron mass times the fine structure constant. Spoken slowly for voiceover. Radius equals 1 over m, sub e, times alpha, times fundamental constants. I'm folding into the sentence, if the electron's mass were 0, that radius would blow up to infinity, and bound states would not form the way we know. No stable atoms, no chemistry, no molecules with memory. The electron gets its mass from its Yukawa coupling to the Higgs field. Coupling equals mass times root 2 divided by v, with v equal to 246 GeV. So the mere fact that chemistry exists is already a testimony that a field with a non-zero vacuum value permeates space, and that the electron does not refuse its handshake. I think that's a clean bridge from esoteric scalar to your table is solid. There's a complementary story in radioactive beta decay, the slow heartbeat of elements in stars and in Earth. Beta decay proceeds through the weak interaction, whose carriers, the W and Z bosons, are heavy, precisely because they ate the goldstone modes of the Higgs field when the symmetry hid. If those bosons were massless, the weak interaction would be long-ranged and utterly unlike what we observe. If they were heavier or lighter by large factors, stellar burning and nucleosynthesis would shift in ways that poison our particular window for life. I'm cautious about anthropic whispers, but I'm not shy about the plain causal chain. Higgs mechanism gives W and Z mass. Mass sets weak range and strength. Weak processes sculpt the nuclear alchemy that builds the periodic table we inherited. Because you wanted math that can be spoken clearly, let me carry out one compact calculation about the vacuum itself. The Higgs potential, the energy, as a function of the field, has a shape with a low valley where the field rests. In simple words, the energy density at that resting point is roughly lambda times v to the fourth divided by 4. Using the numbers we've already named, v to the fourth is about 3, 0.7 billion in GeV to the fourth, lambda is about 0.13, and dividing by 4 keeps us around 100 million in GeV to the fourth for the raw scale of that contribution. The observed dark energy density that accelerates the universe corresponds to a scale closer to a tiny fraction of an electron volt raised to the fourth. Call it on the order of 10 to the minus 47 in GeV to the fourth. Saying it in one breath, the naive Higgs vacuum energy and the measured cosmic acceleration differ by something like 50 to 60 orders of magnitude. That mismatch is not a rounding error. It's the most severe fine-tuning puzzle in physics, the cosmological constant problem. We believe enormous cancellations occur between the Higgs contribution, other quantum fields, and a bare vacuum term we insert by hand to match observation. Why those cancellations land on the measured spec rather than on 0 or infinity is a live, brutal question. The Higgs is not to blame for the puzzle, but it is a prominent term in the impossible arithmetic that the universe somehow balances. Let me pivot to the electron's heavier cousins, because second generation and first generation couplings are becoming an art form. We have seen the Higgs decay to muon pairs, a stunningly small coupling made visible by patience and luminosity. The charm quark is trickier. Charms live long enough to leave displaced vertices, but not as cleanly as bottoms. Their fragmentation patterns are more democratic, and in the soup of QCD jets at a proton collider, they hide in plain sight. Clever taggers machine learning classifiers that drink in track impact parameters, secondary vertex topology, and soft lepton content are now teasing out charm-enriched samples. The logic is the same sentence we keep repeating. Coupling equals mass times root 2 divided by v. The charm's mass is about 1.3 GeV, roughly 30 times heavier than the Strange and about 10 times lighter than the bottom, so its coupling should lie in the same ratio. Measuring that is not merely checking a box. It's testing whether the Higgs treats families universally according to mass, or whether some subtle flavor principle bends the rule for the light generations. There's one coupling so tiny, it's almost a poem, the Higgs electron Yukawa. Plug the electron mass, roughly half an MeV, into that simple formula, and you get a coupling near 3 in 10 million. That is why we do not produce the Higgs resonantly in electron-positron collisions the way we might at a muon collider. The direct S channel is suppressed by that minuscule number. But if you go to a muon collider, the muon mass is 105 MeV, the coupling is around 6 times 10 to the minus 4, and suddenly it's conceivable to sit right on the 125 GeV resonance and scan across it. If the beam energy spread can be squeezed down toward the MeV scale, we could in principle measure the Higgs width directly rather than infer it indirectly. Technically ferocious, scientifically irresistible. I want to keep unitarity in the frame because it motivates more than one particle. We talked about longitudinal W scattering and how the Higgs cures the energy growth. That cancellation is delicate. It requires the coupling of the Higgs to W pairs to have just the strength the standard model predicts. Differential measurements of WW scattering at high energy vector boson scattering with forward jets and central leptons are therefore not merely background to something else. They're a direct test that the unitarity restoration works with the couplings we have inferred. If there are small, effective field theory operators that tilt those couplings by a few percent, the growth at high invariant mass of the diboson system will show a gentle, speakable slope. In voice-friendly math, you can recite deviations scale like energy squared over lambda squared. So plot event yields versus the diboson mass, and listen for the low rising hum at the high end. Let me add a more philosophical but concrete note about renormalization, because it's the quiet machinery that keeps the numbers honest. Quantum fields are not static sculptures. Their couplings run with energy. The Higgs self-coupling lambda, the top Yukawa, and the strong coupling all change predictably as you dial the energy scale up or down. We use the renormalization group equations you can imagine as a weather forecast in energy space to evolve measured couplings from one scale to another. That's how we talk about vacuum stability. We take the measured Higgs mass and top mass at the weak scale, run lambda to far higher scales and ask whether it stays positive or dips negative. The answer seems to hover near the line between absolute stability and metastability, with the deciding vote cast by the top mass in its second decimal place. I won't pretend the universe cares about our aesthetic preferences for stability, but I will say this: the sensitivity of that inference to a single input turns precision metrology at colliders into a cosmological lever. Detector truth matters just as much, and I want to narrate one subtlety that's actually beautiful. In the two-photon channel, the Higgs peak sits on a smooth background of diphoton events from ordinary QCD processes and from jets that masquerade as photons. The Higgs line is narrow, in reality natural width, a few MeV, but our detectors see a convolution, the intrinsic line smeared by instrumental resolution. We cannot resolve the natural width directly. Our calorimeters have resolutions of 1% or so at those energies, which is orders of magnitude broader than a few MeV. So when you look at the bump, you are seeing the detector's fingerprint, not the particle's own. To learn about the width, we resort to off-shell tricks at higher masses, where an off-shell Higgs can contribute to ZZ or WW pairs. The rate there relative to on-shell production whispers the width to us. It's an inferential dance, but an honest one, and it exemplifies how theory and instrument embrace. I want to talk about the sign of interference, because It's a place where the Higgs teaches subtle lessons. The decay to two photons proceeds through loops, W boson loops that contribute one sign, top quark loops that contribute the opposite sign, with the W loop dominating. The net amplitude is the difference. If a new heavy charged particle existed, say a vector-like lepton, the amplitude would pick up an extra term. The total rate could tilt up or down by a few percent. So when I say we have measured the diphoton rate to be consistent with the standard model within uncertainties, I mean we've constrained entire families of hypothetical charged particles that would have left their fingerprints in that interference. Not seen is also a result. And interference is one of the most discriminating not seens in the business. Flavor off the diagonal is another knife edge. The Higgs could, in principle, decay to a muon and a tau if the Yukawa matrices aren't perfectly aligned. We have searched for that and set upper limits at the sub% level for that branching ratio. Translate that. Any misalignment in the lepton sector must be tiny, or the principle of minimal flavor violation is at work. On the quark side, a decay to bottom plus strange is buried under oceans of background at a hadron collider, but at a clean electron-positron Higgs factory, the door cracks open. Every null result tightens the web of what the Yukawa textures can be. Every positive hint would rewrite the chapter on how fermion masses arise. Light. Long-lived exotica deserve a spotlight because the Higgs is a natural portal. Imagine a light scalar that mixes by a tiny angle with the Higgs. A 125 GeV Higgs could then decay into two of these light scalars, which themselves travel a centimeter or a meter before decaying to pairs of muons or pions, leaving displaced vertices like punctuation marks off the beamline. Traditional triggers weren't great at catching such oddities, but modern experiments are building dedicated triggers and reconstruction optimized for displaced signatures. A single clean observation of two displaced dimuon pairs from a common origin would be a Rosetta Stone for a whole class of hidden sector models. The fact that we haven't seen it yet translates to a bound on the mixing angle that you can say out loud, the angle must be small. The Higgs is mostly itself. Because you asked to keep the math in plain text, let me pin down one more rate to yield reality check. Suppose your inclusive Higgs production cross-section in a given run is around 50 picobarns, and your integrated luminosity is 3000 inverse femtobarns. The scale of the high luminosity LHC's ambition, multiply the two. 50 times 3000 gives 150,000 Higgs bosons before selections in that run period. Now fold in branching ratios in words. 2 photons at roughly 2 in 1,000 gives around 300 raw diphoton decays. 2 Z bosons to 4 leptons at a few in 10,000 gives on the order of tens of events. Bottom pairs at nearly 60% gives tens of thousands, but with ferocious backgrounds. After acceptance and efficiency, you keep fractions of those. That arithmetic tells you which questions will mature into precision and which will remain whispers even after a decade of heroic running. It's why we supplement the Proton Collider with the promise of electron-positron factories, absolute normalizations, clean environments, and model-independent inferences that a Hadron Collider struggles to deliver. I have to return once to the hierarchy anxiety because it refuses to let go. Scalar masses are sensitive to high-scale physics in a way that vector masses and fermion masses are not. Their quantum corrections do not decouple kindly. The Higgs mass, sitting comfortably at 125 GeV, looks tuned if you believe the standard model extends up to the Planck scale with nothing to cushion the corrections. Supersymmetry, composite Higgs, extra dimensions, these are not flights of fancy, they are structured attempts to provide that cushion. The null results so far push the simplest versions into contortions, but the principle remains sound. Either a protective symmetry or an explanatory structure is missing from our picture, or the cosmos is tuned and we must learn to live with it. I'm open to all three possibilities. I only insist that we phrase the puzzle in numbers anyone can hear. Loop corrections try to lift the Higgs mass by amounts proportional to the square of the cutoff. Keeping the physical mass, small demands cancellations to many, many decimal places unless asymmetry forbids the dangerous terms. Let me close this stretch by tightening the two questions you began with into a single breath I can stand behind. What is the Higgs boson? It is the quantized ripple of a field whose non-zero vacuum value hides electroweak symmetry and allows elementary particles to carry rest mass without breaking the gauge structure that makes predictions possible. It is a scalar, spin zero, even parity, with couplings to fermions proportional to their masses and to vector bosons proportional to their roles in the broken symmetry. Has it been discovered yet? Yes, first announced in 2012 by two independent experiments, since then tested across production modes and decay channels with a consistency that borders on audacious. I am satisfied enough to teach it. I am restless enough to keep measuring. I think the path ahead is precision as a searchlight, self-coupling from double Higgs production, second-generation UKAWAS from charm and muons honed to crisp numbers, vector boson scattering angles as unitarity truth serums, rare and invisible decays squeezed toward their natural bones, and eventually clean recoil measurements at an electron-positron Higgs factory that nails absolute couplings. If the Higgs is a perfect minimalist, we will know in percent-level detail if it's the visible tip of a deeper symmetry or a hidden sector. The first cracks will show up as slants in lines and whispers in rates, not as thunderclaps. Either way, the lesson remains steady. A field fills space. Its value gives mass. Its ripple is real, and we learn to hear it. I want to take the question, why 125 GeV, and turn it into an honest meditation, because that number is both beautifully ordinary and strangely suggestive. In the standard model, the Higgs mass is not predicted. It's an input we measure and then use to compute the rest. But once we measure it, the web of consequences is tight. A lighter Higgs, say under 100 GeV, would have been seen long ago at LEP from the way Z bosons recoil against missing mass or from direct decays. A much heavier Higgs, say above 200 GeV, would have left different fingerprints in precision electroweak data and would have made longitudinal WW scattering harder to tame without additional structure. At 125 GeV, the model is internally consistent, unitarity is rescued in exactly the way we checked, and the pattern of branching ratios is a delicate balance where photons are rare, bottom quarks are abundant, and 4-lepton golden events are precious but clean. I think the number is not a prophecy but a pivot. It puts us near the metastability boundary for the vacuum when combined with the top mass. It keeps decays to heavy new states kinematically closed. It leaves us in a regime where precision is the scalpel that matters most. Let me translate metastability into a pocket computation you can speak. The running of the Higgs self-coupling lambda with energy is governed by renormalization group equations where the top Yukawa coupling pulls lambda down as energy rises and gauge couplings push it up more gently. With a Higgs mass around 125 GeV and a top mass around 173 GeV, evolving the equations upward suggests lambda crosses zero at energies well above the electroweak scale, opening a lower distant valley in the potential. In Mike-friendly words, if lambda turns negative, our valley is only locally deepest, not absolutely. Quantum tunneling is permitted, but absurdly slow for our parameters. Change the top mass by a GeV or two, yes, just one or two, and the crossing can move or vanish. That sensitivity is why the exact definition of top mass used in experimental extractions matters. A Monte Carlo mass parameter is not the same as a short distance mass in a precise renormalization scheme. We work to convert between them, and every decimal place that gets cleaned up changes the story of the vacuum from metastable to possibly stable within errors. It's not doom, it's a lever arm that connects collidometrology to cosmic temperament. Because numbers only sing when they're tied to yields, I want to keep anchoring expectations in arithmetic you can hear. Expected events equal luminosity times cross-section. For a rule of thumb, at current proton collider energies, inclusive Higgs production is of order tens of picobarns. Multiply that by integrated luminosity, hundreds to thousands of inverse femtobarns across a long run, and you land on tens to hundreds of thousands of Higgs bosons created. Then break the cake into slices by branching ratio spoken in plain text. Bottom pairs roughly 6 in 10. W pairs roughly 2 in 10. Gluon pairs around a tenth. Z pairs a few in 100. Tau pairs a few in 100. Photons 2 in 1,000. Muon pairs 2 in 1,000,000. After acceptance and efficiency, each of those becomes a thinner sliver. And the analysis craft is allocating attention where the combination of cleanliness and yield can sharpen a coupling by a few percent rather than a dozen. I want to hold the detector craft in focus because the Higgs exists for us only insofar as our instruments are literate. Pile up dozens of overlapping proton-proton collisions in the same bunch, crossing sprays, low-energy tracks, and calorimeter deposits everywhere. We now subtract pileup in jets by grooming algorithms that remove soft wide-angle radiation, and we use per-particle pileup identification to downweight tracks unlikely to come from the hard interaction. Photon identification leans on shower shapes, how narrow and symmetric the electromagnetic cascade is, on the absence of tracks pointing to the cluster, and on isolation, the quiet ring of little energy around the photon. Muon momentum scales are anchored by resonances like the J, psi, and the Z. Electron energy scales are tuned the same way. If I sound like I'm counting rivets, it's because at percent level, precision every rivet matters. 0.1% drift in the electromagnetic energy scale will bias the Higgs mass. An unmodeled tail in jet misidentification will counterfeit a rare decay. The Higgs as an idea is robust. The Higgs as a measurement is an accumulation of 1,000 discipline choices. Let me step back to the mathematics you asked to be spoken, this time in the grammar of coupling fits. Experimentalists often summarize results as signal strengths, mu, which are the observed rate divided by the standard model expectation. When we split by production mode and decay mode, we solve a little inference puzzle. Rates equal production cross-section times branching ratio, and branching ratio equals the partial width to a given channel divided by the total width. If one coupling changes, it can raise a production cross-section while also changing the total width and thus diluting branching ratios elsewhere. The clean way to speak this is we fit all relevant couplings at once, allowing correlated shifts, and we constrain them with a tapestry of channels. In effective field theory language, I can say, slowly, deviations scale like energy squared over lambda squared, so differential distributions, invariant masses, transverse momenta. Rapidity gaps are not garnish. They are the magnifying glass for new physics hidden at heavy scales. There's a question I love because it forces me to keep my humility straight. Could the Higgs be composite rather than elementary? If the Higgs were a bound state of a deeper strong dynamics, like a pion is in QCD, it could be naturally light as a pseudo-Goldstone boson, with its mass and couplings protected by symmetry. The consequence would be small deviations in couplings that grow with energy, partners such as vector-like quarks to unitarize amplitudes, and resonances in vector boson scattering. We have pushed hard on those signs, and found none yet, which squeezes the parameter space. But I can't elevate, not yet, to never. A composite Higgs, with partners just beyond our current energy reach and deviations at the few percent level, remains viable. Precision is the judge. Patience is the strategy. I want to return to flavor in the lepton sector because it's a pristine testbed for mischief. We've limited the branching ratio for Higgs decays that violate lepton flavor like muon tau to well under 1%. In plain speech, if the Higgs flips lepton flavor at all, it does so very rarely. On the quark side, the story is murkier because of backgrounds, but a clean lepton collider would let us tag charm and strange more confidently in association with a Z and watch for Higgs decays into uncommon pairs. The rule we keep reciting, coupling equals mass times root 2 divided by V, implies a strict hierarchy. A measured tilt, even a gentle one, would be a beam of light through the fog that hides the origin of Yukawa textures. Unitarity again, but with a different face. The cancellations that keep longitudinal vector boson scattering well behaved are not merely a yes or no, they can be tested as a function of energy. In vector boson scattering events tagged by forward jets and central leptons, we build the invariant mass of the diboson system and look for an upward curl in the tail compared to the standard model prediction. Effective operators that tweak the Higgs vector couplings would generate exactly that pattern. So a sentence of math you can say slowly: the differential cross-section at high mass equals the standard model piece plus a small correction proportional to mass squared divided by lambda squared, with a coefficient fixed by the operator in question. Fitting that tail is a microscope for scales beyond our direct reach. Because you asked for math that is friendly to a microphone, let me state two identities I carry around. First, the relation between the weak scale and Fermi's constant. V equals 1 divided by the square root of 2 times G sub F. Spoken with pauses, V equals 1 over the fourth root of 2 times GF. Plug in the measured GF from muon decay. You get V about 246 GeV. Second, the cubic self-coupling of the physical Higgs in the standard model equals 3 times the Higgs mass squared divided by V. Say it slow. Lambda 3 equals 3 times m sub h squared divided by V. If we can measure double Higgs production precisely, we are effectively asking whether that sentence is exactly true in nature or only approximately true with a small correction from higher scales. The quartic self-coupling lurks a step further out, practically out of reach now, but even tiny windows on it would tell us about the anharmonicity of the potential, the stiffness of the vacuum when pushed hard. Now, about future machines, not as talismans but as complements. A circular electron-positron collider running near 240 to 250 GeV would produce Higgs bosons, mainly in association with Z bosons. Reconstruct the Z cleanly, count the recoil mass on the other side, and you get a model-independent tally of Higgs events regardless of how the Higgs decays. That anchors absolute couplings without the degeneracies that haunt hadron colliders. A linear collider can polarize beams, flipping left and right-handed couplings to isolate specific structures. A muon collider, if we tame beam-induced backgrounds and squeeze the energy spread, could sit on the Higgs resonance and scan it directly, an S-channel privilege denied to electrons by their tiny Yukawa. Each program is not merely more, it's different axes in parameter space with different systematic landscapes. Together, they triangulate truth. I want to lean into theory uncertainties, because precision only means something if the theory predictions that meet the data are as crisp as the measurements. Higgs production through gluon fusion depends on Parton distribution functions and on higher order QCD corrections. We compute cross-sections at next to leading order in QCD, with resumations for certain kinematic corners, and we assign uncertainties from missing higher orders by varying renormalization and factorization scales in correlated ways. In voice-ready language, when we quote a rate, we attach a theory error, born from our best estimate of uncalculated terms. And that error matters when experiments are precise to a few percent. If experimental error bars shrink below theory error bars, the bottleneck moves to the blackboard. That is already happening in some channels. It's a good problem to have. A quieter but dear piece of the story is unfolding literally, the process of correcting measured distributions for detector effects to recover particle level or parton level truths. We build response matrices that encode how true values smear into reconstructed ones, then invert those matrices carefully with regularization to avoid amplifying noise. The reason to care is that global fits need results that different experiments can compare on common ground. When I say the high PT tail of the Higgs spectrum looks standard model-like within uncertainties, that statement has passed through unfolding, through correlated systematics, through theory corrections. It is not a picture snapped with a phone. It is a painting restored by conservators who leave the brushstrokes honest. Let me use everyday physics again as an anchor, because it keeps abstractions from floating away. The Bohr radius I mentioned scales inversely with the electron mass. If the electron mass changed by even 10%, atomic sizes would change by 10%. Chemistry would be rewritten, reaction rates would jump, stellar opacities would shift. The Higgs electron coupling fixes that mass through the simple sentence we've used. Coupling equals mass times root 2 divided by V. In the standard model, V is fixed by G, F. The electron mass is measured and put in. The coupling is then implied. If we ever saw the Higgs decay to an electron pair at the ludicrously tiny rate implied by that coupling far beyond present reach, that would be a direct handshake between the field in the vacuum and the electrons that make matter. Rigid. For now, the chain of inferences is already tight enough to act with confidence. There is a field, it has a value, it makes the electron heavy enough that atoms are small, and chemistry exists. I want to linger on interference, because it's the subtlest kind of argument the Higgs lets us make. In the two-photon decay, the amplitude has contributions from a W loop and a top loop with opposite signs. The W wins, but the top subtracts a noticeable fraction. A new heavy charge scalar, or vector-like lepton, would add its own loop. Even if that new particle were too heavy to create directly, its virtual effect would tweak the two-photon rate by a few percent. So when we measure that rate to say 5% and find it consistent with expectation, we've silently said no heavy charge states with sizable Higgs couplings up to a certain scale. The Higgs, in other words, vetoes company it never meets face to face. Has it been discovered yet? Yes. And more than yes, it has been weighed, its spin and parity traced, its most important couplings sketched with increasing sharpness, its rarest accessible decays glimpsed, its self-interaction poked indirectly, and its conspiracies with the W and Z in vector boson scattering tested for the right cancellations. What is it? It is the smallest ripple of a field with a non-zero vacuum value that hides electroweak symmetry and lets particles carry mass without breaking the logic that makes quantum gauge theories calculable. I think the road ahead is not paved with thunderclaps, but with decimals. Measure the muon and charm couplings until mass proportionality is not a slogan, but a row of numbers. Squeeze invisible and exotic, branching fractions until a few percent becomes a few per milli or a few per 10 to 1,000. Chase double Higgs until the cubic self-coupling is either the textbook number or very slightly not. Map vector boson scattering tails with effective field theory eyes for slopes that grow like energy squared over lambda squared. Then, when different machines, proton, electron, muon, sing the same song with different voices, we'll know whether the 125 GeV scalar is the exact minimalist we wrote down, or merely the first visible petal of a deeper symmetry. Until then, I keep three short truths close enough to say, in my sleep. A field fills space, its value gives mass, its ripple is real, and we learn to hear it. I want to peel back one more layer on what it means to see a field through a particle, because the Higgs is the cleanest case study of that translation from continuum to quanta. A field is continuous, defined at every point. A particle is a discrete excitation that carries energy and momentum. In quantum field theory, those are not two different things. They are two vocabularies for the same entity. When I say the Higgs boson is the ripple of the Higgs field, I'm not being poetic, I'm being literal in the mathematics. The field operator is expanded into creation and annihilation operators that add or remove single quanta. And the vacuum expectation value is the part of the field that does not annihilate the vacuum. The visible ripple rides on an invisible pedestal. If the pedestal was zero, the gauge symmetry would be manifest and the weak bosons would be massless. Because the pedestal is non-zero, the symmetry is hidden and the W and Z are heavy. I think, the discovery in 2012 let us hold the ripple in our hands long enough to read the pedestal's inscription. There is a practical, almost carpentry level lesson hidden in that abstraction. We measure the pedestal by watching how the ripple pushes on other quanta. The value V equals 1 over the 4th root of 2 times the Fermi constant, that's the quiet handshake between the weak force measured in muon decay and the field value that gives the weak boson's mass. Say it slowly because it rewards attention. Take the Fermi constant, GF, multiply by 2, take the 4th root, invert it, and you have roughly 246 GeV. Everything we do with Higgs couplings leans on that number. When I write coupling equals mass times root 2 divided by V, I'm putting the pedestal into every handshake with a fermion. When I write that the W and Z masses are proportional to the gauge couplings times V, I'm turning pedestal height into carrier heft. The pedestal is not an adjustable aesthetic. It is a measured scale with fingerprints across weak processes that predate the LHC by decades. I want to put the strong force and the Higgs in the same picture because it clarifies what each is responsible for. Lattice QCD is our abacus for the strong interaction. We discretize space-time into a grid, put quarks on sites and gluons on links, and compute numerically how bound states emerge from the nonlinearity of the gluon field. Those calculations can turn quark masses, small numbers set by Yukawa couplings to the Higgs, into hadron masses we can compare with experiment. The up and down quark masses enter as input parameters, a few MeV each, while the proton mass emerges near 938 MeV, primarily from gluon field energy and quark kinetic energy. The Higgs gives the quarks their baseline masses. QCD traps them and inflates that baseline into the bulk of everyday matter. If you dialed the Higgs up or Higgs down couplings a bit, lattice QCD would translate that dial twist into shifts in hadron masses and nuclear binding. Chemistry would tilt, stars would burn differently, and the periodic table would wear a different mask. The levers are separate but entwined. The Higgs sets rest masses. The strong force amplifies them into the heavy furniture of reality. I also want to make the electroweak unification point tangible, because the Higgs sits exactly where two forces share a roof. Above the electroweak scale, the weak and electromagnetic interactions are aspects of a single gauge structure. Below that scale, after the Higgs field turns on its vacuum value, the forces split into a massive short-range weak force and a massless long-range electromagnetic force. The weak mixing angle, an angle you can say as theta W, tells you how the original gauge bosons combine to form the photon and the Z. The relation between the W and Z masses and theta W at tree level, MW equals MZ times the cosine of theta W, is a crisp echo of that unification. Loop corrections bend it slightly, and those bends depend on the top mass and the Higgs mass. That is why, even before 2012, precision data kept whispering that the Higgs should be light. The whisper was not mysticism, it was the algebra of loops nudging a trigonometric identity. Because precision is a theme, let me talk about how we build global pictures without overpromising certainty. The modern language is the standard model effective field theory, where I write every higher dimensional operator consistent with the symmetries and fit their coefficients to data. Each coefficient has units of 1 over a heavy scale squared. In microphone-friendly math, a deviation in a Higgs coupling at energy E scales like E squared divided by lambda squared. If E is a few hundred GeV, and we see no deviation larger than a few percent, then lambda must be several TeV or higher for the operators that would have modified that process. The power is that I can fit many processes together. Higgs production and decay, vector boson scattering, triple gauge couplings, even top quark processes, because the same higher dimensional fingerprints recur across them. The humility is that I'm only as good as my basis choice and my control of correlations. Still, when a dozen channels all point to small or absent coefficients, I'm allowed to say no large, simple new physics near the TeV scale that talks loudly to the Higgs. Quiet does not mean absent. It means shy or heavy. I should keep returning to unitarity because it's the most physical way to feel necessity rather than taste. Longitudinal W scattering wants to blow up with energy. The Higgs exchange cancels the bad growth. This is not a hand-wavy story. It's an amplitude-level identity you can check term by term. If the Higgs coupling to W pairs were even a few percent off, the cancellation would be imperfect, and the invariant mass distribution of die-boson pairs at the TeV scale would start to arc upward beyond the standard model curve. That's why measurements of vector boson scattering with forward jets and central leptons matter. They are high-energy lie detectors for the Higgs's unitarizing role. I like that this connects a philosophical rule: probabilities cannot exceed 1 to a literal plot in a paper with error bars and a tail. Let me anchor the self-coupling again, because it is the shape parameter of the vacuum, and shapes are memorable. In plain words, the cubic self-coupling lambda 3 equals 3 times the Higgs mass squared divided by V in the standard model. Plug in 125 GeV for the mass, square it to get about 15,000 in GeV squared, multiply by 3 to get about 45,000, then divide by 246 GeV to land near 180 GeV, spoken slowly. The cubic self-coupling has the dimensions of mass and is roughly 180 GeV in this normalization. We do not measure it directly, we infer it through the tiny rate of double Higgs production. If the true coupling were, say, 20% larger or smaller, the double Higgs rate in kinematic shapes would shift in ways we can calculate. The high luminosity LHC will push the uncertainty on this coupling down. A dedicated Higgs factory, followed by a higher energy proton collider, could turn that inference into a crisp test. The stakes are exact. Is the Mexican Hat Valley cut by a textbook quartic or dented by higher scale physics? I want to say something concrete about rare decays, because rare is where many surprises prefer to hide. Higgs to Z plus photon is loop suppressed and therefore sensitive to the same interferometers that make the 2-photon channel a sniffer for new charged particles. Higgs to 2 muons is suppressed by the tiny muon Yukawa, and therefore an acid test of mass proportionality for second-generation fermions. Higgs to invisible probes, whether there is a neutral particle, perhaps a dark matter candidate, that couples to the Higgs weakly enough to have escaped every other net. Each of these rates is small. Each of them yields leverage out of proportion to the count. If Z plus photon lands exactly on the standard model, a whole class of exotic charges is pushed further away. If muons line up, mass proportionality is more than a slogan. If invisible is squeezed below a few percent, then Higgs portal models must whisper rather than talk. Because you asked for math in spoken form, let me carry out a simple yield estimate that ties many strands together. Start with an inclusive Higgs production cross-section of roughly 50 picobarns at a given energy. Multiply by an integrated luminosity of 3,000 inverse femtobarns, the end state goal of the high luminosity LHC, and you get 150,000 Higgs bosons produced. Multiply by the branching ratio for 2 photons, about 0.2%, and you expect around 300 raw diphoton decays. Acceptances and efficiencies, trim that to perhaps 100 clean events. For double Higgs, the cross-section is roughly 1,000 times smaller, so you start with hundreds instead of thousands over the same luminosity. And after cuts, you're living on tens distributed across many final states. That arithmetic is why patience is not a virtue but a requirement in Higgs self-coupling studies. It's also why a clean lepton collider with model-independent recoil counting is so attractive. You count ZH events first, then you apportion them among decays without arguing about absolute normalizations. I want to emphasize detector literacy once more because the Higgs peak exists in data only, because energy scales are shepherded to sub% fidelity. Photon energy scales drift as crystals age. Muon momentum scales drift as magnetic fields breathe, and alignment microns relax. We pin them with standard candles Z to 2 leptons, J, psi to muons, pi 0 to 2 photons, and track them in time. Jet energy scales are calibrated with gamma plus jet and Z plus jet events, where momentum balance gives a lever arm. B-tagging efficiencies are measured in control samples, where a muon in a jet tags a semileptonic B decay. All of that invisible work is the scaffolding under the one-number headlines. When I say the Higgs mass is measured to a few tenths of a GeV, I am leaning on thousands of hours spent convincing silicon to remember where it sits, and crystals to remember how bright they should be. There's a different frontier that thrills me because it closes a loop between theory, simulation, and hardware. Differential measurements unfolded to particle level and compared to predictions with full uncertainty accounting. The Higgs transverse momentum spectrum at high PT is particularly telling because it is shaped by whether heavy virtual particles run in the loops that generate gluon fusion. If a new heavy-colored state existed with a strong Higgs coupling, the high PT tail could bend ever so slightly. In voice-ready math, the deviation, again, scales like energy squared over lambda squared, and the energy proxy is the Higgs transverse momentum. So we fit the tail, propagate detector, smearing through response matrices, and report bin-by-bin cross-sections with correlations. The act sounds dry. The consequence is that a smooth tail can sentence entire menageries of hypothetical particles to exile at scales we cannot otherwise touch. I also want to be honest about theory uncertainties, because they are part of the currency of truth. Gluon fusion cross-sections are computed to very high order in QCD, but not to infinite order. We estimate the uncertainty from missing higher orders by varying renormalization and factorization scales in correlated ways. We propagate parton distribution function uncertainties drawn from global fits. We decorate predictions with electroweak corrections where they matter. When experimental error bars shrink below theory error bars, we either push the calculations a notch higher or accept that the bottleneck sits on the blackboard for the moment. This is not an embarrassment. It is the sign of a mature field where experiment and theory hand the baton back and forth. Let me close this turn by braiding the two questions that started us with the arc I've tried to sustain. What is the Higgs boson? It is the quantized ripple of a field that fills space and never turns off, whose non-zero vacuum value hides electroweak symmetry and allows elementary particles to carry rest mass without wrecking gauge consistency or unitarity. Has it been discovered yet? Yes, decisively since 2012, And the story since has been a decade-long tightening. Spin zero, even parity, couplings proportional to mass for fermions and to gauge charges in the right way for vectors, a narrow intrinsic width inferred through off-shell tricks, a pattern of rare decays gradually coming into focus, and first stabs at its self-coupling through double Higgs. I think the remaining adventure is precision as discovery, charm and muon couplings nailed to the few percent level, vector boson scattering tails, scanned for gentle slopes, invisible and exotic decays pressed until percent level ceilings crack or hold, and the vacuum stiffness read from double Higgs, with enough certainty to decide whether our Mexican Hat Valley is textbook clean or slightly dented by deeper physics. The answer to has it been discovered is the easy yes. The answer to what is it exactly is the patient song of decimals we are still learning to sing. I want to press on the idea that the Higgs is both a book we've opened and a ruler we now use to measure the margins of reality, because that's how precision becomes a searchlight. Start with the simplest measuring stick I can speak in one breath. If a Higgs couples to a fermion with strength equal to mass times √2 divided by v, then the ratios of couplings are just ratios of masses. Said slowly for the mic, the muon to tau coupling ratio should equal the muon mass divided by the tau mass. The bottom to tau ratio should equal the bottom mass divided by the tau mass. These aren't poetic slogans, they're testable equations. Every time we add data and the points fall on that straight line through the origin, we're not merely confirming a diagram, we're confirming that the vacuum pedestal V we inferred from the Fermi constant really is the same pedestal that fermions are leaning on across 3 generations. I think that unity, the same V in weak decay and in Higgs Yukawas, is one of the soft miracles of the Standard Model. Let me ground that unity with the weak scale's most intimate partner, muon decay. In words you can say slowly, the muon's mean lifetime is set by Gf, the Fermi constant, through a simple power law. Lifetime is roughly 1 over G f squared times the muon mass to the 5th, up to known numerical factors and radiative corrections. We measure the lifetime exquisitely. From it we infer Gf. From Gf we infer V, with that compact sentence you've heard me recite. V equals 1 over the 4th root of 2 times G, F. From V, together with the Higgs mass, we infer the quartic lambda that shapes the Mexican Hat Valley, lambda roughly equal to the Higgs mass squared divided by 2V squared. When the numbers land, they don't merely land, they interlock. If one were very off, if V from muon decay disagreed with V from the W and Z masses after loop corrections, or if the pattern of Higgs couplings refused to scale with mass, we'd have felt the rattle years ago. The quiet fit is not boring, it's discipline turning into knowledge. Now I want to put the mass from Higgs rule next to the mass from QCD rule in a sentence that stays true in your ear. For quarks and leptons, the rest mass in their Dirac terms equals Yukawa coupling times V divided by √2. For hadrons like the proton, most of the mass equals energy stored in gluon fields plus the kinetic energy of confined quarks, all counted as mass by E equals mc squared. Those two statements live peacefully side by side. If you dialed V down by 10% while somehow holding all dimensionless couplings fixed, electron mass would shrink by 10%, atomic radii would grow by 10%, chemistry would tilt, and beta decays would speed up or slow down as the W mass shifted with V. But the proton's mass would barely blink, because its bulk comes from QCD dynamics, which care less about V and more about the strong coupling scale, lambda QCD. The universe is mercifully modular. One knob sets fermion masses and weak scales, another sets the strength and scale of the strong interaction. The Higgs sits on the first knob. Lattice QCD teaches us the second. Because you asked for math that a voice can carry, let me say two compact identities that capture electroweak bones. First, at tree level, W mass equals G times V over 2, and Z mass equals V over 2 times the square root of G squared plus G prime squared, where G and G prime are the SU2 and U1 gauge couplings. Spoken gently, MW equals GV over 2 MZ equals V over 2 times the square root of G squared plus G prime squared. The ratio gives you the cosine of the weak mixing angle. Second, the Higgs vacuum value V fixes the overall strength of weak processes through G, F, which we already tied to V. These salt grain formulas look bland until you realize they're the arithmetic that turned LEP precision and Tevatron top quark measurements into a pre-LHC whisper that the Higgs should be light. LEP nudged M, W, and the mixing angle. The top mass fed the loops. The fits lean toward a small Higgs mass because heavy scalars tug those loop-corrected relations in a predictable direction. When July 2012 arrived, the bump at 125 GeV was not a bolt from nowhere. It was the dot on a meeting point circled by data. Let me talk about line shapes and widths in a way your ear can keep. A particle's natural width, gamma, is the inverse of its lifetime, up to Planck's constant. Lifetime equals h bar divided by gamma. The Higgs has gamma of a few MeV, giving a lifetime around 10 to the minus 22 seconds. We cannot see that width directly in on-shell decays because detector resolution smears the line by hundreds of MeV, much broader than the intrinsic few MeV. So we measure the width by a clever detour. We compare on-shell and off-shell regimes in processes like Higgs-mediated ZZ production above the ZZ threshold. On-shell rates scale like couplings squared divided by gamma. Off-shell rates scale like couplings squared without the 1 gamma penalty. The ratio whispers gamma. If the Higgs had exotic invisible decays enlarging gamma substantially, the whisper would quiver. It hasn't. The upper bounds say the invisible slice, if present, is small. Small doesn't mean non-existent. Small means we've cornered it to the percent scale at Hadron Colliders and can do even better in a clean lepton machine by counting recoil events model independently. I want to bring interference back because it's the subtlest teacher. Higgs to gamma proceeds through loop diagrams that sum with signs. The W loop is large and positive in a standard sign convention. The top loop is smaller and negative. The net is their difference. A new heavy charge particle would add another loop with a sign set by its spin and couplings. Even if that particle were too heavy to produce, its loop stays. That is the magic. The Higgs lets us veto entire populations of hypothetical charge states with nothing but a percent level diphoton rate and a careful theory error bar. The same logic lives in Higgs to Z gamma, a rarer loop-induced decay that trades a photon for a Z. If you're listening for new charge scalars or vector-like leptons, these are stethoscope channels, clean, soft, and damning. Because experiment is a cathedral of details, I want to tour one scaffold you rarely hear about: unfolding. Data are born as smeared, cut, and triggered distributions. Theory predictions are born as parton-level lines on a screen. To compare them honestly, we either fold predictions through detector response into Reco space, or we unfold data back to particle space. The second route requires a response matrix, a probability distribution that a true value lands in a reconstructed bin and a regularized inversion, so that statistical noise doesn't explode. Speak it simply, we learn the smearing from simulation tuned with control data, we build the matrix, We invert carefully, and we carry the correlations forward. When I say the high transverse momentum tail of the Higgs looks standard model-like, that sentence sits on unfolding, on PDF uncertainties, in gluon fusion, on resomations that tame soft gluon radiation, and on photon energy and muon momentum scales chained to Z peaks over years of running. The serene statement is built on noisy labor. Let's pivot to self-coupling with numbers you can keep. The standard model predicts a cubic self-coupling lambda 3 that equals 3mh squared, divided by v. With m, h near 125 GeV and v 246 GeV, lambda 3 lands around 180 GeV in this normalization. Double Higgs production rate depends on lambda 3 through interfering diagrams, a triangle diagram with the self-coupling and a box diagram without it. Those diagrams interfere destructively in the standard model, making the rate small. If lambda 3 were higher, the triangle would lean harder. If lower, it would slacken. The total cross-section and shapes would bend accordingly. In mic-friendly math, the cross-section equals box squared plus triangle squared, plus 2 times box times triangle. So a shift in lambda 3 changes both the triangle squared and the interference term. That's why we don't only count total events, we slice by kinematics where the interference swings are more pronounced, like high invariant mass of the Higgs pair. The high luminosity LHC will turn this from a rumor into a number with bars, a higher energy proton collider, or a lepton collider with dedicated channels would make it crisp. I should say something about CP symmetry in the Higgs sector, because it is a hinge between particle physics and the cosmic matter excess. In the standard model, the one Higgs doublet setup makes the observed Higgs a CP even scalar. If there were a CP odd admixture, even tiny, it would twist angular distributions in decays like Higgs to Z, Z to 4 leptons, and would show up in production asymmetries, especially in vector boson fusion, where polarization information leaks into jet angles. We frame this in effective operators you can vocalize, a CP odd term proportional to the dual field strength tensor times the Higgs can tilt the rates and shapes. Measurements so far lean heavily toward pure CP even, but the bounds still allow a small odd whisper. A genuine odd component would be a signpost toward the extra CP violation we crave for electroweak baryogenesis in extended Higgs sectors. The same phases could feed electric dipole moments of electrons and neutrons, where tabletop experiments already set breathtakingly tight limits. That triangle Higgs CP, baryogenesis, EDMs, is a clean map, push any corner, and the other two move. Now a word about theory error bars in the channels that carry our sharpest scalpels. Gluon fusion is known to next to leading order in QCD with soft gluon resomation. Vector boson fusion and associated production are known at comparable precision with electroweak corrections. We estimate uncertainties by scale variations, PDF ensembles, and matching scheme choices. Say it plainly. When experiments quote a 3% uncertainty on a coupling, they're allowed to do that, because the theory rate they divide by also carries a 3% envelope we trust. If experimental precision dives below theory precision, the blackboard becomes the bottleneck, and we climb one order higher, or we adopt more robust observables whose theory is crisper. I want to fold the Higgs into cosmology with one sober arithmetic exercise because it shows both the reach and the restraint of our knowledge. The naive vacuum energy from the Higgs potential near the minimum scales like lambda times v to the 4th over 4, plug in lambda around 0.13 and v 246 GeV, and you get a stupendously large energy density in GeV to the 4th units. The observed dark energy density is closer to 10 to the minus 47 GeV to the 4th. The difference is 50 or 60 orders of magnitude. We reconcile this in our equations by allowing a bare cosmological constant that cancels almost everything, leaving the tiny observed sliver. I do not know why the cancellation lands with that precision. No one does. The Higgs is not the cause of the problem. It is a prominent term in the impossible sum. The honesty is to say the cosmological constant problem is a separate, deeper puzzle that any ultimate theory must face, squarely. Because you asked for math in plain text, let me hand you one more pocket formula for significance beyond the back of the envelope S over root B. The Asimov approximation writes the discovery z-value as the square root of 2 times the quantity S plus B times line 1 plus S over B minus S. Speak it like this: Z equals square root of 2 times open bracket S plus B times the natural log of 1 plus S over B minus S close bracket. It reduces to S over root B when S is much smaller than B, and it behaves sensibly when S is not tiny. Real analyses go beyond it. They fit shapes and profile nuisance parameters, but this formula carries intuition you can narrate without algebra on the screen. Let me not neglect the second generation, because turning proportionality into percent numbers, there is the heart of the decade. Higgs to muon pairs has been observed at the right ballpark. Charm is coming, through charm taggers trained on displaced vertices and soft lepton content, and through channels where kinematics reduce background. The expectation is simple in words. Charm coupling equals about 1.3 GeV times root 2 divided by V, which puts it an order of magnitude below bottom. If we land that number within, say, 20%, and it hugs the proportionality line, a huge class of flavor non-universal alternatives will be squeezed. If it bends off the line, even gently, the road forks toward flavor symmetries or radiative mass generation models that break the naive rule for light generations. Small deviations will not be noise, they will be letters. I want to give the muon collider dream one more clear minute because it's the most direct Higgs ruler conceptually. In an electron-positron collider, S-channel Higgs production is suppressed by the microscopic electron Yukawa. You mainly produce ZH pairs. In a muon collider, the muon Yukawa is roughly 200 times larger, so an S-channel scan across the Higgs resonance becomes possible in principle. If you can make the beam energy spread of order the MeV scale intrinsic width, you don't infer the width, you measure it as a line shape. That would break the current reliance on off-shell gymnastics and turn the width into a directly plotted curve. It's technically ferocious because muon decays seed backgrounds and cooling muon beams is a heroic art, but the physics payoff is so clean that it sits like a star on the roadmap. Let me bring it home by looping your 2 original questions through everything I've said until they feel finished in the mouth. What is the Higgs boson? It is the quantized ripple of a field that never turns off, whose non-zero vacuum value hides electroweak symmetry and lets elementary particles carry rest mass without breaking gauge consistency or unitarity. It is a scalar with spin 0 and even parity. Its couplings to fermions scale with their masses. Through the simple sentence, coupling equals mass times root 2 divided by V. Its couplings to W and Z are set by the same V that fixes the weak scale. Its lifetime is so short that we only ever see its footprints in clean pairs of photons, Zs, Ws, bottoms, taus, muons. Has it been discovered yet? Yes, in 2012 by 2 independent experiments, and yes, each year since with tighter couplings, rarer decays, sharper differential spectra, and first stabs at its self-interaction. The live questions are no longer existential, they are metrological. Is the self-coupling exactly 3m, h squared over v, or nudged by heavy scales? Do second-generation couplings sit exactly on the mass line or tilt with a secret principle? Do vector boson scattering tails stay flat or curl gently with energy squared over lambda squared? Does the diphoton interference leave no room for heavy charge ghosts, or a sliver? Does the invisible width hide a percent of dark matter's handshake or none? I think the path to those answers is not a single thunderclap, but a decade of disciplined decimals, more luminosity at the LHC, better calibrations that keep photon and muon scales honest to the per milli, theory predictions that climb one rung higher, electron-positron factories that count ZH events without assumptions, and perhaps one audacious muon machine that scans the resonance like a jeweler's loop over a gem. Until then, I keep 3 short truths close enough to recite in my sleep because they stayed true through every turn of this conversation. A field fills space, its value gives mass. Its ripple is real, and now we use that ripple as a ruler to see if nature drew the rest of the picture with the same steady hand. If I have to bring everything we've traced into one continuous breath, I'd start where the physics is most physical and end where the numbers close the circle. The Higgs boson is the smallest ripple of a field that never turns off, and that field's non-zero value is what lets the electroweak symmetry hide so that the W and Z can be heavy and the photon can be light. That single sentence threads through what we see in detectors, what we infer in equations, and what we live with in chemistry and stars. I think the power of this story is that it's not merely an elegant diagram, it's a web of mutually checking facts. We measure the Fermi constant from muon decay and translate it by a one-line identity you can say slowly on any mic into the vacuum value V of the Higgs field. V equals 1 over the 4th root of 2 times GF, which lands near 246 GeV. We fold that V into simple proportionalities. Coupling equals mass times root 2 divided by V, and suddenly electron mass, muon mass, tau mass, bottom mass, top mass all become not just labels but responses to the same background field. We use the same V to set W and Z masses at tree level as M, W equals GV over 2, and M, Z equals V over 2 times the square root of G squared plus G prime squared. And we see small loop-borne bends in those relations that already pointed, even before discovery, to a relatively light scalar. The mathematics whispers one answer. The detectors heard the same word in 2012. Has it been discovered yet? Yes. And the yes has matured from a sighting into a characterization. The bump at 125 GeV in diphotons and in 4 clean leptons was the stake in the ground. The years since have tightened the ropes into a measured outline. Spin zero, parity even, couplings to fermions that scale with mass as predicted, couplings to vectors that restore the delicate cancellations required by unitarity in high-energy WW scattering. The lifetime is so short that the particle flickers away in about 10 to the minus 22 seconds. You translate that spoken as lifetime equals Planck's constant divided by width, and the width is only a few MeV. We do not resolve that width directly in on-shell decays because detector resolution smears the line by orders of magnitude. Instead, we infer it by comparing on-shell and off-shell regimes in ZZ and WW final states, where the dependence on the width changes from inversely proportional to independent, and the ratio whispers a number. Small, precise whispers are the grammar of this era. I want a conclusion that remains honest to scale, so let me lay the arithmetic plainly, because it grounds all. Expected events equal luminosity times cross-section. If inclusive Higgs production is of order tens of picobarns at a given energy, and your integrated luminosity is hundreds to thousands of inverse femtobarns over a long run, you expect tens to hundreds of thousands of Higgs bosons produced. Then the cake slices by branching ratio. You can speak in whole words. Bottom pairs are the fat slice at roughly 6 in 10. W pairs around 2 in 10. Z pairs a few in 100. Tau pairs a few in 100. Gluon pairs a tenth. Photons 2 in 1,000. Muon pairs 2 in 1,000,000. After acceptance and efficiency, those numbers thin, and the analyses become craft. B tagging with displaced vertices, forward jet tagging for vector boson fusion, tight isolation rings for photons, stitch calibrations for muon momentum and electron energy anchored on Z peaks. Nothing here is a hand-wavy legend. It is rivets and response matrices, triggers and unfolding, nuisance parameters profiled in global likelihoods. It is also a philosophical rule made literal on plots. Probabilities must add to 1, and amplitudes that try to grow too fast with energy are tamed by the exact pattern of Higgs exchanges the standard model prescribes. If you want the shortest chain from field to flesh, hold the Bohr radius and the Higgs electron coupling in the same palm. The characteristic size of hydrogen scales inversely with electron mass times the fine structure constant. If the electron mass was 0, atoms would not bind into familiar finite shapes. The electron's mass equal to its Yukawa, coupling times V divided by √2, ensures that atoms are small enough for chemistry to be rich and stable. Your table is solid because a scalar field that never turns off lends the electron just enough inertia to be held close to the nucleus by a photon that the Higgs does not touch. The other side of the coin is the weak interaction. The W and Z are heavy precisely because the symmetry is hidden, and their heaviness sets the pace of beta decay, stellar burning, and the nuclear alchemy that seeded the periodic table. The Higgs is not an ornament placed after the fact. It is a precondition for the world to look anything like this. I want to say something decisive about the why this mass unease, because the hierarchy problem isn't a vibe, it is a calculation. Quantum loops try to pull the Higgs mass parameter upward toward the highest energy scale where the theory remains valid. Keeping the physical mass at 125 GeV, if the theory runs clean to the Planck scale, looks like exquisite cancellation between a bare parameter and loop corrections, fine-tuning unless a principle forbids the dangerous sensitivity. Supersymmetry, composite Higgs ideas, extra dimensions are structured responses to that calculation. They have not yet shown their faces where we have looked hardest. So the pressure is on the simplest variants, but the question remains sharp. I can live with tuning. I can live with a protective principle we haven't guessed. I can live with heavy structure just beyond reach. I cannot live with pretending the arithmetic isn't real. The honesty of the Higgs era is that we phrase the puzzle in numbers that anyone can repeat out loud, and then look for where nature offers a clue as a percent level tilt rather than a dramatic thunderclap. The precise future I want is not romantic. It is procedural and it is beautiful. Second generation couplings must be nailed. The muon channel has crossed the threshold into sighting. The charm channel is within reach with clever tagging and associated production where kinematics help. Each success fortifies the core rule coupling equals mass times √2 divided by V with concrete numbers, and shrinks the space for alternatives that treat light families differently. Double Higgs production must graduate from rumor to measurement so that the self-coupling can be read from data. Spoken in microphone math, the rate depends on the square of a box amplitude plus the square of a triangle amplitude, with lambda 3 and their interference. If lambda 3 differs by enough, shapes and totals bend predictably, especially in the high invariant mass tail of the Higgs pair. Vector boson scattering with forward jets and central leptons must be pushed deep into the TeV tail, where energy squared over lambda squared deviations from higher dimensional operators would draw a gently rising line if the Higgs couplings are even slightly off. Rare loop-induced decays like Z plus gamma must be sharpened, because they are stethoscopes pressed to the chest of hypothetical charged particles that can hide too heavy for direct production, yet still leave their interference fingerprints. Invisible decays must be squeezed with both proton data and clean recoil counting at lepton machines, because a percent level doorway into dark matter through the Higgs would be revolutionary in a whisper. There is also the quiet cosmological lever that runs through metrology. The running of the Higgs self-coupling lambda with energy is pulled down by the top Yukawa and nudged up by gauge couplings. With today's best fit masses, lambda drifts towards zero at scales far above the weak scale and may tip slightly negative, which translates to a vacuum that is metastable on absurdly long timescales. Shift the top mass by a GeV in a short distance scheme, and the sign at ultra-high scales may change. That is not esoteric. It is a reminder that weighing a quark in a collider, with definitions careful enough to talk to, renormalization, feeds into a statement about the temperament of emptiness across the cosmos. I think that is the right kind of romance. Not slogans, but levers that run from microns of silicon alignment to eons of vacuum fate. Let me confront, for completeness, the elephant in the cosmic room, the vacuum energy problem. If you plug the Higgs numbers into the naive potential energy density at the minimum lambda times v to the fourth divided by 4, you get a ridiculous energy density compared to the observed dark energy, off by 50 or 60 orders of magnitude. We do not sweep that under a rug. We acknowledge that our bookkeeping includes a bare cosmological constant that cancels almost everything, and we admit that we do not yet know why the cancellation lands where it does. The Higgs is not the cause, but the Higgs is an explicit term in the impossible sum, and any deeper theory worthy of the name must be able to tell that story without hand-waving. Precision in the Higgs sector will not solve this on its own. It will, however, fence theories of everything with hard numbers they must fit. So I end where I began, with the two questions asked plainly and answered without hedging. What is the Higgs boson? It is the quantized ripple of a field that fills all of space, whose non-zero vacuum value hides electroweak symmetry and allows elementary particles to carry rest mass while preserving the gauge structure and unitarity that keep a quantum field theory predictive. It is a scalar with spin zero and even parity. It couples to fermions in proportion to their masses and to W and Z in exactly the way needed to tame high-energy scattering. It is narrow, living for about 10 to the minus 22 seconds. It decays in a pattern that within current precision mirrors calculations built decades before we turned the LHC on. Has it been discovered yet? Yes, decisively since July 4th, 2012, by two independent experiments that saw consistent bumps in clean channels, and have since expanded those bumps into a network of measurements that all point to the same object. The live questions are not existential, they are precise. Is the cubic self-coupling exactly 3m h squared over v, or nudged by heavy scales? Do second-generation Yukawas sit on the proportionality line or tilt? Is there a percent of invisible width hinting at a dark handshake? Do differential spectra at the high-energy edge trace perfectly the standard model slopes, or curl by energy squared over lambda squared with a coefficient that earns a name? My conclusion, spoken in the cadence I've carried on purpose, is simple and earned. A field fills space. Its value gives mass. Its ripple is real. We proved the ripple exists. We weighed it. We sketched how it talks to the rest of the cast. Now we are using that ripple as a ruler, pressing it against every seam in our map, listening for a deviation as small as a percent and as meaningful as a new continent. I am satisfied enough to teach the Higgs as fact. I am restless enough to measure it until the decimals either sing the same clean note or reveal a harmony beneath the melody we thought was solo. If the universe chose to whisper rather than shout, we built the microphones for whispers, and the Higgs is where we hold them.